C++ is absolutely atrocious. First of all, there's like 20 different ways to initialize a variable, and there's so many rules and edge cases around initialization that somebody wrote a 300-page textbook solely on this one topic. Just about everything in C++ is a mess. Consider the task of printing something to the console. Most languages have a simple print function to do that, but in C++, you have to use this gross angle bracket syntax. We did eventually get a normal print function in 2023, only 40 years after the inception of the language, but sadly, most of the industry is still stuck on older versions of C++, so it's unlikely that you'll get to use cutting-edge stuff like this in practice anytime soon. Here's another example of C++'s ugliness. Consider the task of generating a random number. In Python, you just call random.randint, and you're done. Whereas in C++, you have to create a random device and a standard MT19937, and then you have to go on a side quest to figure out what an MT19937 is, then create a standard uniform int distribution, and then inject the MT19937 inside the uniform int distribution, and then finally we get a random number. Although this code isn't too hard to read, it's difficult to conjure up from memory when you actually need it. Writing a benchmark is even worse, by the way. Here's an example of doing it in C++ versus JavaScript. There are ways to make the C++ code less verbose, with the auto keyword and using declarations, but you can't do the former for member variables and you shouldn't do the latter in header files because it'll pollute the global namespace. So you're inevitably stuck with the verbose version of the code in many situations. Casting in C++ is another thing which is obnoxiously verbose in comparison to other languages. In Java, you just put things in parentheses. It's simple, concise, and clean. In C++, you have to use static cast. It's incredibly annoying and tedious to type this out every time you want to cast something, and it's a terrible eyesore that bloats up the code. Consider any function or formula where you need to perform a cast multiple times. It makes it hard to read. And static cast doesn't work in all scenarios. Sometimes you have to use dynamic cast, reinterpret cast, const cast, or bit cast, depending on the context. A common theme I see with C++ beginners is that they get annoyed with reading and writing static cast, so they create an alias for it. But creating aliases for language keywords is really bad practice, because other developers won't be familiar with your version of the language, so it's best not to do this. And that's the thing that's so jarring about C++. Correct C++ code often just looks wrong, especially to beginners, and it takes a long time to build up an intuition for what good C++ code is supposed to look like. Eventually, you end up accepting the fact that in C++, the terse solution is almost never the correct solution. Another example of something that's dead simple in other languages but complicated in C++ is creating a global variable. Have fun watching this 20-minute video on how to do this fundamental basic thing that would take 2 seconds to learn in any other language. The problem is that you have all these keywords like extern, const, inline, static, and const expr, and they all mean different things in different contexts, and you have different idiomatic combinations of them that also have their own rules and meanings in different situations. And C++ aggressively repurposes existing keywords in inconsistent ways. The static keyword, for example, has about 3 or 4 use cases depending on how you count it. The first one is to make variables persistent between function calls. The second is to share class variables across different instances, or create class functions that exist independently of any instance. But the third use case is a complete semantic non sequitur. It's used to make functions private, or rather inaccessible from outside the CPP file that they're defined in. I really wish that they would have used the word private or internal instead of static. This illustrates how C++ keywords oftentimes don't even describe what they do. The inline keyword is also a misnomer. In the past, it was used to inline functions, which is an optimization trick to get the compiler to copy the code from the function definition directly into each call site, rather than performing a normal function call. This helps avoid the overhead of function calls like setting up the stack, passing the parameters, and return value handling. But nowadays, compilers are smart enough to do this automatically, so using the inline keyword for this purpose doesn't have any guarantees. These days, inline is used to resolve issues regarding the one definition rule. The funny thing here is that using inline on a function does the exact opposite of using inline on a variable. In both cases, they solve one definition rule related issues, but an inline function leads to potentially many separate instances of the function across the binary, whereas an inline variable makes sure that there is only a single instance of the variable in the whole binary. Additionally, you can also make a namespace inline. This is typically used for library versioning. The list of weird edge cases and caveats just goes on and on. It never ends. The keyword const expr has its own set of nuances, like how const expr functions are inline by default, but const expr variables are not inline by default. Also, you can't use const expr on all types, only on const expr compatible types. And every version of C++ has different rules on how you can use const expr. Everything in this language feels hacked together, even the inheritance system. In Java, you have an explicit interface keyword to create interfaces. But in C++, you have to use the virtual keyword in every function, and then do this weird thing where you make each function equal to 0. And only then is it considered an interface. This is a very unusual syntax. And strangely enough, when you override functions in a derived class, the override keyword is purely optional. C++ is a crazy language, and learning it can be a daunting task for beginners. There's about 50 integer types, and the size of these types varies depending on which compiler you use and the target machine hardware. Notice how it doesn't say that int is 16 bits, it says that it's at least 16 bits, but it could also be 32 bits. And you have to know these rules about how on any given system the size of a short will be less than or equal to an int, which will be less than or equal to a long. Even the operating system which you use changes things. On Windows, long is 32 bits, even if it's 64-bit Windows. This is for backwards compatibility reasons. On 64-bit Linux, long is 64 bits. The names are also just so verbose and ugly. I hate typing long. I wish we could all just agree to use something terse like I64 in the case where we want 64 bits. Again, you could technically create your own aliases, but it's ill-advised. And I hate how fixed-width integer types have an _t suffix. I mean, come on guys, we're not in the 90s anymore. Beginners also find it weird how getting the size of standard library data structures returns a size t instead of an integer, which can also be of various sizes depending on the hardware. At some point, you'll inevitably run into the 7 different character types and wonder what they all mean and why a character would ever even need to be signed or unsigned like a number, and why an unsigned char is often used to represent bytes and binary data, and also what's wchar and what's the difference between a standard string and a W string, and what are all the issues pertaining to that. This stuff might make sense to you if you're an experienced developer, but if you're a beginner, it's incredibly confusing and it raises a million questions. Furthermore, there's so many different ways to do the exact same thing in C++. There are 2 different function syntaxes, the traditional one and the trailing return type syntax. They don't even look like the same language. You can also get function-like behavior using a struct, and if you don't like parentheses, you can use square brackets instead. Const is another source of confusion. It's used for indicating that a variable's value is constant. It tells the compiler to prevent the programmer from modifying it. But counterintuitively, writing mutable const is completely valid C++ code. And if you really want, you can remove the constness of a variable by casting it away, but that's considered bad practice. Additionally, many beginners are surprised to find out that when you make a member variable const, you can no longer assign your object to another object. Another quirk of const is that it can go on either side of the type, but both do the exact same thing. There's no point to this. There should only be one correct way to do this to avoid confusion, because pointers can also be const. So it takes a bit of practice getting used to figuring out if the const keyword applies to the value of the type or the pointer. The general rule of thumb is to read it from right to left. But this is stupid and unintuitive because most humans read from left to right. If you're still confused, the spiral rule might help you out. It's easy stuff, man. You'll get the hang of it. Moving on to formatting, C++ developers just can't seem to agree on how to format and style their code. Should you use snake case or camel case? Should the opening curly brace go on a new line or not? Should the private section of a class be written at the top or the bottom? Should you prefix variables based on their type or context? What's the best way to split a line of code if it's too long? Should you put each parameter on a new line or just divide the function in the middle? Should you use the virtual keyword in derived functions or not? Should you use eastconst or westconst? Should references and pointers stick to the type or the name? Which extension should you use for header files? How about C++ files? Also tabs or spaces? And if so, how many? It's like every single C++ codebase is an entirely different language. You could spend your entire life working on, say, Unreal Engine C++ projects, and then struggle to do anything else because of all the custom macros and wrappers around it that you'd have to unlearn. When I first set out to learn C++, I made it a goal of mine to study the Google C++ style guide. However, many seasoned developers cautioned me against it, explaining that the guide is designed for Google's aging codebases and tailored to address Google-specific challenges, many of which are irrelevant to modern codebases outside of Google. There's also the official C++ core guidelines, but historically it's always been very incomplete. As of recently, it seems like it's getting better, but nevertheless, most real-life codebases just don't follow this, so you're stuck writing C++ in a completely different way depending on which codebase you're contributing to. Moving forward, nearly everything in the C++ standard library that is important is poorly named. In Java, you have simple, accurate, self-descriptive names for the fundamental containers, like ArrayList, LinkedList, HashSet, and HashMap. In C++, the most commonly used container is called vector. This is kind of like Java's array list. But it's a horrible name because a vector is usually thought of as being a physics concept, which represents a magnitude and a direction. Even the designer of the standard template library, Alex Stepanov, confessed that the name was a mistake. Additionally, if you want to use a hash set or hash map in C++, you might mistakenly reach for standard set and standard map. But these are not what you think they are. They're implemented as balanced binary trees and give you logarithmic lookup time complexity, as opposed to constant time complexity, which is what you would have expected based on the name. If you want constant lookup time complexity, then you have to use unordered set and unordered map. But honestly, you shouldn't be using these either, and I'll explain why in just a moment. Even the methods of these fundamental data structures are poorly named. Many containers, for example vector, have an empty function. It's hard to tell at first glance if this function is a question, which checks if the container is empty, or if it's a verb, which empties the container. A better name would have been .isEmpty. The standard library is filled to the brim with confusing, incomprehensible function names like standard stoy, install, and stuff, and stud, and stold. And I know that some of these were probably inspired by their C counterparts, and they're just abbreviations of types, but cryptic names like this can be very intimidating to beginners, and it makes everything seem more complicated than it needs to be. Even the most commonly used terms, idioms, and best practices in C++ are terribly named. For example, RAII, which stands for Resource Acquisition, is initialization. This is a super important idiom in C++, but the name makes it so much more confusing than it actually is. It just means that when an object goes out of scope, its resources should be freed automatically. So make sure you put the resource releasing logic in the destructor. A much better name would have been Scope-Bound Resource Management, or CADRE, which stands for Constructor Acquires, Destructor Releases. Too bad neither of them caught on. Another example of bad naming is the CRTP idiom, which stands for Curiously Recurring Template Pattern. The name has very little to do with what it means. Curiously recurring just refers to the fact that the guy who coined the term, James O'Kaplian, stumbled upon this pattern on various occasions and was intrigued by it. Hence the name Curiously Recurring. This has nothing to do with what the pattern actually does. It only describes his impression of the pattern, which is useless in helping people understand what the pattern is. It should have been called the Static Polymorphism Template Pattern, or Compile Time Inheritance. It would have been far more self-descriptive and helpful to beginners. C++ also has something called standard monostate, which is intended to be used inside variants to represent an empty state. The name monostate is the most pretentious, deliberately abstruse thing I've ever heard. It's absolutely wild to me that they chose that name. They should have called it standard empty or blank or void or something. There's also a feature called deducing this in C++ 23. Basically, when we call an object's member function, under the hood, the object is implicitly passed to the member function, even though you don't see it in the parameter list. Deducing this lets you make the parameter explicit. This has various advantages that I won't cover. My main gripe is that it should have been called something more self-descriptive like explicit object parameters. And the remove function in the standard library doesn't even remove anything. It just moves the elements to the end of the container. As C++ evolves, the naming conventions only get more and more confusing. Many new features, which are meant to be improvements of old deprecated ones, have less than ideal names. The standard library has a mutex wrapper called standard lockguard, but it's not able to lock multiple mutexes. There was a proposal to extend lockguard to include this feature, but that was found to break backwards compatibility, so they made a new mutex wrapper called standard scoped lock. Developers have been critical about the choice of this name. It's hard to remember which one is the old version and which one is the new version based on the name alone. Some developers argue that it should have been called lockguard 2 to make it more explicit that it's the newer version. In the same vein, standard thread and standard function also have issues, but because they can't break backwards compatibility, they made a jthread and copyable function, which contain the fixes. Again, the chosen names completely fail to communicate that these are the newer improved versions. They probably should have been called thread 2 and function 2 respectively. Instead, we're stuck memorizing which versions to use and which not to use, and newcomers have no intuitive sense of what is deprecated and what isn't. And as the language evolves, I won't be surprised to see that we'll have versions 2, 3, 4, 5, and 6 of many of these features. The only thing more nauseating than the naming conventions, however, is dealing with header files. Header files are just awful. Pretty much every time you create a C++ file, you also need to create a corresponding header file, and you need to make sure that they're synchronized at all times. This is a blatant violation of the don't repeat yourself principle. If you change the parameters of a function in the CPP file, you also need to make sure to update the contents in the corresponding header file to match. And God forbid, if you use the wrong parameter names in the header file, it'll compile just fine without letting you know. For example here, where it says width then height, versus the actual implementation which uses height and then width. Or here, where the stock quantity and the price are mixed up. The maintenance overhead that comes along with using header files is exasperating, and it's easy to imagine how this can lead to bugs, not to mention all the redundant typing that's involved. If you create a class that requires a constructor, you end up writing the class name 4 times, twice in the header file where you've declared the class, and 2 more times in the CPP file where you define the constructor. And then finally, you can begin writing the implementation. Writing things over and over again is annoying. Compare this to almost any other language like Java, for example, where the exact same thing is half the amount of work. The other problem with header files is that they bloat up your project directory. An application that would have otherwise taken 100 files to complete now requires 200 files in total because of the corresponding header files. This also means that you have twice the amount of files to check in pull requests and code reviews. It just adds so much unnecessary mental fatigue to dealing with this language. And there's so many different ways of organizing your project structure. Some devs keep their header and CPP files in the same folder. This is typically used in applications. Other developers keep them in 2 different folders. This is typically used in libraries. There are other structures as well that I'm not going to cover. The point is that it would all be so much simpler without header files. Perhaps the worst thing about header files is that when you include them, the compiler just stupidly copies and pastes the contents of the file into the line where you've included it. This means that if you've included something more than once due to a transitive dependency, you now have the same types and functions defined more than once. This breaks the one definition rule and gives you a compiler error. To fix this, you need to tell the compiler not to include something again if it's already been included. You do this with header guards, which you have to put inside every single header file in your entire codebase. It's exhausting, and developers online argue incessantly about which technique to use because there are at least 2 ways to do it. The first is with include guards, which are more verbose because it requires 3 separate preprocessor directives and necessitates that you create and maintain a unique macro name. Usually this name is based on the file name. Don't forget to update it if you change the file name. The other technique is to use pragma once, but for some reason this isn't recognized by the C++ standard, so it's not the officially agreed upon way. And because it's not in the standard, some people say that you should never use it, whereas other people say that you should use both together at the same time. All this incessant arguing ignores the fact that this issue shouldn't even exist in the first place. The compiler should just know to include a file only once, and if you don't like that, there should be a way to opt out, and not the other way around. Developers sometimes try to justify the existence of header files by arguing that they represent the public interface to your code. However, classes which are declared in headers have their private variables and functions exposed there too. This is a leaky abstraction. Private implementation details don't belong in a public interface, but since they exist there, you have to include those dependencies in the header file. This means that anyone who includes your header file now by extension also ends up transitively including the files related to the implementation details of the class. To add insult to injury, if you change a private member variable, you have to recompile everything that includes that header, even if that change is purely internal and semantically irrelevant to client code. There are some solutions to this, but not really. There's a design pattern called Pimple that can be used to hide the implementation details entirely inside the CPP file, but it makes things more complicated and it comes with a performance penalty. And honestly, in a well-designed language, private variables like this should be hidden by default without all this unnecessary work. C++ in general has very weird ways of hiding implementation details. If you want to isolate your code from the outside, you can use an anonymous namespace, or you can make your function static, as we discussed earlier, or you can do both at the same time. And as I've stated before, I would have preferred a private keyword for this purpose instead. You might also see people try to hide their implementation details by putting them in a detail or implementation folder and corresponding namespace. But there's no built-in mechanism in C++ to prevent others from accessing the code in these folders. Anyone can easily include these implementation files and use them anyway. The user has to know which files are okay to include and which are not, usually by reading documentation written by the creator of the library, which may or may not exist. Another major flaw of C++'s header file system is how much it pollutes the autocomplete suggestions. As I mentioned earlier, the include preprocessor directive is just a glorified copy and paste operation, so it dumps all the types, functions, and other symbols from the header file directly into your code, which in turn pollutes your autocomplete suggestions with functions and types from all over your codebase. Consider the situation where you include a header that includes 10 more headers, and each of those headers include 10 more headers, and so on and so forth. You end up with 1,000,000 symbols from the entire dependency tree flooding your autocomplete and making it useless. I can hardly rely on using tab to autocomplete my code because it's replete with irrelevant suggestions. And this is why developers hate it when noobs include windows.h. It imports like another 1,000,000 symbols into your project. And macros make everything even worse. Macros in C++ are basically search and replace commands that happen before your code is actually compiled. If you write to define size 100, you're telling the compiler to replace every instance of size with 100. Macros don't respect the type system or scoping rules, and they have no semantic awareness, and they operate indiscriminately across all code which is downstream in the include chain. This means that if you include a header with macros, those macros can hijack your code because those search and replace commands are now active in your code, whether you like it or not. It's like inviting someone into your house and they secretly start rearranging your furniture without telling you. Imagine that you have a function sendMessage, and then you include windows.h. Windows.h has a macro for sendMessage, which ends up overriding your sendMessage function. Or imagine if somebody writes a macro to make private public, which is sometimes used naively for writing tests. Now all your private variables and functions are exposed. Given the fact that the header inclusion system dumps all the symbols directly into your code, the probability of there being name clashes is much higher than in modern languages that have proper module support. This is something that C++ inherited from C, and has led to the creation of another problematic feature, which is namespaces. If you're moving to C++ from C, namespaces look like a fantastic feature, because the solution to name clashing in C was to prefix your functions with your project name. But in C++, you use namespaces instead. Wonderful. This is great. But if you're moving to C++ from any other language, this is a serious downgrade, because namespaces make the code look hideous. Modern languages don't force you to write namespace prefixes everywhere. In modern languages, name clashing occurs far less frequently because they don't use header files, so you deal with naming ambiguities as they arise. And yes, I know that you can use the using keywords to omit namespace prefixes in C++, but then you're back to square one, with the name clashing issues due to the header inclusion system and symbol dumping. So best practices basically force you to use namespace prefixes nearly everywhere. Aesthetically, the worst thing about namespaces is that they incentivize programmers to choose the shortest names possible, typically 2 or 3 letters. Obviously, if a language forces you to write namespace prefixes everywhere all the time, you're gonna end up picking obscure shorthand names for your namespaces. The end result is that C++ codebases are riddled with abstruse, cryptic, unpronounceable abbreviations and arbitrary letter mashups that are difficult to parse through and understand. Functionally, however, namespaces have a very big problem that almost nobody talks about. In C++, symbol lookup happens in ever-expanding scopes. This means that first it checks the function, then the current namespace, and then the parent namespace, and then the global namespace. This means that if someone adds a namespace that matches part of your namespace hierarchy, it can silently change which symbols are found during compilation. This means that people can break your code without directly touching your code. Let's say you have a log function, which is inside the company namespace, and you use it in a team namespace, which is nested inside the company namespace. Everything works as you'd expect, but not for long. If someone comes along and adds another log function inside company team, it'll hijack your call to log. Now you're executing this new log function. Logging is a benign example, but it's easy to imagine how this can lead to security vulnerabilities. In this example, the authentication system silently switches to using an insecure hash, which was made for testing purposes. The implication here is that you shouldn't use deeply nested namespaces in your C++ projects. This is very counterintuitive, because while nested namespaces might seem to provide better code organization, they actually increase the risk of name collisions due to C++'s lookup rules. Realistically, you should only have one distinct top-level namespace per project. This imposes limitations on how you organize your code and makes you realize how deeply flawed C++ is for creating and maintaining large codebases. I really can't stress how bad the whole namespace system is. Beginners are often taught that namespaces are a feature of C++, when in reality they're just a fragile workaround for the fundamental design flaws of header files that it inherited from C. Namespaces are a terrible patch, which results in an unnecessary syntactic burden and footguns that you don't encounter until you're 10 years into the development of your codebase. Not to mention, macros don't even respect namespace boundaries, so you still have that issue to worry about. It's crazy to think about how much pain and suffering is caused by header files, simply because the creators of C didn't have the foresight to predict that C would be used in large-scale codebases. This single decision to introduce header files in the 1970s as a solution to the technical constraints of their era, limited memory and single-pass compilation, has tortured millions of developers across generations. We're talking billions of dollars in wasted development costs, maintenance overhead, and bug fixes, and millions of hours of collective human psychological anguish. It's truly a crime against humanity, and a crime against developers. At some point, you have to come to terms with the fact that C and C++ were never designed to be used for large software projects, and if you do choose to use them for that, you'll be fighting with them every single step of the way. That being said, I do have a little trick that I use to reduce the syntactic burden of C++ and make it way easier to read, without breaking any best practices. Strangely enough, I never see anybody talking about this trick for some reason. Maybe I'll cover it in the next video, so make sure to subscribe if you're interested. Anyways, back to header files. There are so many other issues that I haven't covered, like how they completely fail on circular includes with some irrelevant error message that doesn't help at all. But the final header-related topic that I want to touch on is the compile times. C++ compile times are completely unacceptable, due to the fact that including stuff just copies and pastes the code. Everything that you include in each CPP file will get compiled from scratch every single time. So if you include string in your codebase in 1,000 different CPP files, the compiler will stupidly compile string 1,000 times. And keep in mind that the string header also includes a bunch of other stuff, which includes a bunch of other stuff, and all that needs to get compiled again and again. This is an outrageous waste of CPU cycles, energy, and time. There is a hack to fix this. It's called a precompiled header. This is a special header file which you can put all your most used includes to have them compiled only once. So now all you have to do is include the precompiled header, and you're good to go. But honestly, precompiled headers feel like a hack. In fact, the entire language feels like a broken mess with 1,000 hacks littered everywhere to get anything to work reasonably well. Precompiled headers can be perplexing for beginners. In the past, Visual Studio used to automatically create a PCH file for you when you created a new project, but it confused beginners so much that they now omit it in newer versions. These days, it's an opt-in feature. There's actually so much theory about how to speed up compilation, it's like a science of its own. There are code organization strategies, build system optimizations, compiler optimizations, hardware solutions, development practices. The list just goes on and on. Modern C++ tries to fix the issues created by header files with the new modules feature that's meant to handle everything like a modern programming language would. But the language is so complicated that compiler developers are having a hard time implementing it. For a long time, only Microsoft's compiler had support for C++ modules, and even now as others have started to support it, there are still a lot of issues and bugs that need to be worked out. Even if everything is fixed in the foreseeable future, it'll still probably take a minimum another 10 to 15 years for modules to receive wide adoption. According to this website, modules won't be ready until the year 2547. So as far as you're concerned, you're still going to need to know how to do things the old way. And in the meantime, we're going to be stuck in a messy transition period, where most libraries still use headers, so your code is going to have a weird mix of header includes and module imports. Speaking of modern C++, when you first start learning C++, people often tell you that you gotta learn modern C++, but when you Google what is modern C++, you end up on this post from like 14 years ago. Surely this answer is outdated. And it is. Furthermore, when you look up tutorials online, you're never sure whether you're being taught old-fashioned C++ or modern C++ or something else. A seasoned C++ developer knows the difference, but a beginner doesn't. This leaves you with an unsettling feeling about whether or not you're just wasting your time watching or reading something that's outdated. This applies to textbooks as well. Effective modern C++ just isn't modern anymore. The other problem is that online tutorials paint a very incomplete picture about how to read and write real-life C++ code. They often miss crucial concepts or fail to communicate how certain features and ideas translate into the real world. For example, you'll learn what a raw pointer is, but not what it means. You'll be taught that it holds a memory address, but there's not a whisper about ownership semantics. Raw pointers convey something very important. They convey that they are non-owning. This has certain implications like how you're not responsible for its lifecycle, and if it's stored in a member variable, depending on the context, you might need to make sure that the enclosing object does not outlive the object that the pointer is pointing to. This requires that you understand concepts like lifetimes and scope and the philosophy that underpins these ideas. Another poorly taught topic is smart pointers. You learn what unique pointers and shared pointers are, but what they don't tell you is that in real life, shared pointers are a code smell. You're supposed to choose unique pointers nearly every time. Shared pointers are for very specific niche situations, like where you have multiple threads sharing some data, and it's not known ahead of time which thread will exit last. Tutorials often teach knowledge but not wisdom, because tutorial creators oftentimes don't have wisdom. They just regurgitate information from other sources to make a quick buck on ad revenue, or to sell a book or course or whatever. A lot of C++ content online is created by people who have probably never worked on a real production C++ code base in their entire life. I see so many YouTube tutorials that were released quite recently yet still teach very outdated practices and principles, and often omit key concepts and ideas. The most popular YouTube videos are just the blind leading the blind. I saw a video that went viral last year called 15 Years Writing C++, Advice for New Programmers. This guy gives the typical feel-good bromides that basically amounts to just be yourself bro and just be patient bro and there's no such thing as a bad line of code, so just take it one step at a time and everything will be okay. But in a subsequent video, he confessed that he doesn't even write C++ at his day job. He was just reflecting on some code he wrote 15 years ago. And this is part of a greater trend that I see on the internet where for some reason, people who don't even write production C++ seem to have such a high opinion of the language. Anytime I see a blog or a video about how C++ is a blast or that somebody loves the language, my immediate thought is that this person is a complete and total noob. I have a very simple assertion to make about C++, and I want to be unequivocally clear about it. If you like C++, then you don't know it well enough. YouTube videos aside, academia suffers from the same problem. The C++ that you learn in school is almost certainly outdated. I remember being taught to use the keyword new and delete in school, but nobody does that anymore. We've had smart pointers for a while. I remember being taught to use pushback on vectors, without any discussions of the advantages of emplaceback. I remember being taught the rule of 3, and then it became the rule of 5, and now it's the rule of 0, and in the future it'll be the rule of something else probably. I remember being taught to use standard endline to insert a new line, but that's slow, it flushes the buffer. You should use the new line character instead, or even better, use standard printline. The list just goes on and on. The language has evolved so much and just keeps continuously evolving that it's hard to truly know what modern C++ even is. Did you mean to learn modern C++, or moderner C++, or modernerist C++, or postmodern C++? What are we even talking about here? Initially, C++ 11, which was released in 2011, was the first version that was called modern C++. It introduced smart pointers, lambdas, and move semantics. But now the word modern is a moving target, which is used vaguely to describe any version between 11 and the most recent one. Right now, as of the year 2025, the industry is stuck at about C++ 17, which is 6 years behind the current standard, C++ 23. This is the usual pace at which the industry moves. The reality is that most codebases out in the real world don't immediately upgrade to the latest version, and it's not feasible to rewrite existing code to use the modernerist practices. So you're inevitably stuck learning all versions of C++ so that you can work on both older and newer codebases, and actually be employable. As the language has evolved, its complexity has continued to spiral out of control. There was a proposal to add safety to the language, and the notation included a / and a caret symbol, and some more keywords. It looks like a nightmare to read and maintain, and there's even more syntax and symbols proposed for the new upcoming contracts and reflection features. At the rate we're going, C++ 30 is probably going to look like this. The other problem to be mindful of is that people often confuse C++ with C, probably because C++ initially started out as C with classes, and it's sort of almost like a superset of C, but not quite. And a lot of job postings say that they need someone who knows C/C++, as if the two aren't completely different languages. Furthermore, a common question I see on internet forums is about whether you should learn C before learning C++, as if it's a prerequisite or something. But the answer is a resounding no. Idiomatic C looks very, very different from idiomatic C++. They're different languages. And one of the first things that the C++ community tries to hammer down into beginners' minds is that you shouldn't write C++ like C. Don't use C-style strings, use standard string. Don't use C-style arrays, use standard array or standard vector. Don't use enum, use enum class. Don't use union, use standard variant. There's a whole list of things that you need to remember on what not to do. But the key takeaway is don't ever, ever, ever write C++ like it's C. Unless you're writing C-style C++ and it's okay. You see, some people really like the simplicity of C, and they hate the complexity and feature bloat of C++. So they write a style of C++ that's basically C with just a few C++ features. This is known as C-style C++. And that's the problem with C++. Every single thing that you learn has some sort of surprising edge case which turns out to be super important. You're taught to never write C++ like C. Unless you're working on a C-style C++ codebase, then you have to. You're taught to use static cast whenever you can, but then you learn that you shouldn't do this for enums. Use standard to underlying instead. You're taught that returning a pointer to a local variable is dangerous, because the memory is deallocated when the function returns. But then it turns out that this doesn't apply to string literals, because they have static storage duration and exist for the entire lifetime of the program. You're taught to use standard move whenever you can to efficiently transfer large resources, but then you learn that you should never use it when returning a value from a function, because C++ has an optimization trick called return value optimization, and when you do this, it screws it up. You're taught that private member variables in a class are inaccessible from the outside, but then you learn about the friend keyword that lets you bypass that. You're taught to use const references everywhere for performance reasons, but then you learn that it's actually faster to copy small objects than to pass them by reference. So actually don't pass by const reference if the object is small. Oh, and by the way, you probably don't want to have const reference member variables, because then you open up a whole can of worms with your object's copy and move semantics. So you have to figure out whether you should use a standard reference wrapper or a pointer or a GSL not null or a custom wrapper of your own or something else. The number of edge cases in the language is unfathomable. I've barely even scratched the surface. If you want to learn them all, you can start by reading the spec for C++ 20. It's nearly 2,000 pages long. And if you have any follow-up questions, make sure to visit CPP reference. At some point you'll realize that this is not documentation. It's a cry for help. And since we're on the topic of crying, let's take a look at how to actually build your application. Building a C++ project is a genuinely insufferable experience. The core issue is that there's no standard compiler, no standard build system, no standard package manager, and no standard ABI. The result is a deeply fragmented ecosystem, where every piece is incompatible by default, every setup is a bespoke Rube Goldberg machine, and even the simplest task demands an exhausting amount of boilerplate, configuration, and tribal knowledge. Let's discuss compilers first. According to Wikipedia, there are 31 compilers for C++, but the main three are Microsoft Visual C++, which is the default on Windows, GCC, which is the default on Linux, and Clang, which is the default on Mac OS. Each compiler has different pros and cons in regards to its optimization capabilities, features, tools, and extensions. Compiler extensions are non-standard features added by compiler vendors to provide additional functionality beyond what the C++ standard specifies. These extensions can enhance performance, debugging, or platform-specific capabilities. Some examples of this would be pragmas, built-in functions and intrinsics, attributes, inline assembly, and custom keywords and modifiers. But because it's unique to each compiler, it's often recommended not to use them, or to use them sparingly because they reduce portability. And it's why you sometimes see if defines that look like this, scattered across codebases. It's a way to try to use compiler extensions while maintaining as much portability as possible. Compilers also have a different pace at which they implement new C++ features. In the past few years, MSVC has been the leader on implementing the latest C++ features, with the others lagging behind by a significant margin. But it looks like things have changed abruptly this past year, as Microsoft's priorities seem to have shifted, probably to focus on AI or something. And one of their most prominent C++ experts recently left for Citadel. Around the same time, MSVC has started to really lose its momentum. That being said, one of the biggest issues with MSVC has been that it generates very poor SIMD code in comparison to other compilers, and it has a lot left to be desired in regards to SIMD in general. For example, it doesn't have target attributes to specify which instruction set a particular function should use. The benefit of Clang is that it gives much more friendly errors and warnings compared to the other compilers. It also has excellent tooling, including but not limited to static analysis and formatting. GCC, on the other hand, is the oldest of the three compilers. The main benefit is that it supports a greater number of less popular architectures, but it's slower on Windows than the others. That being said, developers are constantly arguing about which compiler produces the fastest binary. Some devs swear by Clang, but it really depends on your specific use case. Some C++ features are better optimized on certain compilers versus others. If you really care about maximum performance, you'll eventually have to get good at reading assembly so you can read the output of each compiler to see how well your code is optimized. In general, it's best practice to pick two compilers for your dev environment because they all give slightly different warnings. This will help you write higher quality code, and using two different compilers will let you know if you're unintentionally using compiler-specific language extensions. But using more than one compiler means you have more stuff to set up and maintain and be knowledgeable about. Compiler flags introduce a whole other layer of complexity that you have to deal with. There are literally hundreds of flags, many with cryptic names that aren't self-explanatory, and different compilers have different flags for the same functionality, as well as different conventions for their flags. Additionally, some optimizations behave differently across compilers. This makes cross-platform development more frustrating. The various optimization levels can also dramatically change program behavior, sometimes introducing subtle bugs that only appear with certain optimization levels but not with others. And the warning system varies between compilers and versions, and it has unintuitive edge cases like how the flag warning all doesn't actually include all warnings. And missing flags like F stack protector or defortify source can leave your code vulnerable without you realizing it. Managing these flags across different platforms often requires complex build systems. Since C++ doesn't have a standard build system, that's another colossal headache that you have to deal with, because it has led to the proliferation of many different build tools, each with their own syntax, capabilities, and learning curves. On Windows, people typically use MS Build, which comes with Visual Studio. On Mac, people use the Xcode build system that comes with Xcode. And on Linux, developers typically use Make. So what do you do if you're using Windows and your coworker is using Mac? Well, you need to use a meta build system which generates the correct build system based on the platform. But even at this level, the community is fragmented. Some people use CMake, other people use Premake or QMake or Meson or whatever else. And they all have their own unique way of working. There's also meta build systems which generate meta build systems. But thankfully most devs seem to agree that one level of meta is enough. CMake has become the de facto meta build system for modern open source projects, but developers really hate it. It's a horrible build system that was in the right place in the right time and just happened to gain enough momentum to become widely adopted. It uses a terrible custom scripting language that is neither declarative nor procedural. It also has unusual scoping rules, quirky variable handling, and an inconsistent API. The lack of strict typing and the tendency for variables to expand unpredictably makes debugging difficult, and the error messages are not good. It's also evolved significantly over its lifetime, but it maintains backwards compatibility with older, more verbose patterns, so you have multiple ways of doing the same thing. The documentation is awful, and nearly all tutorials are either outdated or focus on trivial examples that fall apart the moment you try to scale them up to a real-world codebase. If you really want to learn CMake, you have to read this 700-page textbook. This is just to learn how to build your application. We're not even at Hello World yet. When you're done reading all that, you'll realize that the library that you want to use is actually configured with Bazel or something. I guess it's time to read another textbook. Keep in mind that CMake is just a build system, not a package manager. Installing and managing third-party dependencies in C++ is another nightmare that you have to deal with. In other languages, installing a library is a no-brainer. It's usually just a single terminal command. In Python, it's pip install, in JavaScript, it's npm install, Rust has cargo add, C# uses .NET add package, and Go uses go get. But in C++, there are a few options and none of them are simple. The first is to try and install a precompiled binary of the library. But here's where the ABI issues come to surface. ABI should not be confused with API. The API is the public interface. It's what you can do with a library. The ABI defines how libraries talk to each other at the binary level. It describes how function calls are made and how data types are laid out in memory. Since there's no standard ABI for C++, each compiler has their own ABI. And the ABIs can even vary between different versions of compilers. This is one of the many reasons why C++ is often criticized for being a poor language for binary distribution. The C ABI is much more stable. That's why C++ developers oftentimes wrap their C++ libraries in C. C is the de facto interoperability layer of systems programming. So even though you only signed up to learn C++, you're inevitably forced to learn at least some C so that you can write and use C++ libraries that are wrapped in a C API. Anyways, to integrate a precompiled C++ library, first you need to decide if you want to do it statically or dynamically. There are pros and cons to each, so make sure to pick carefully. Keep in mind though that not only do they work differently, they use completely different file formats, and those formats vary across platforms. On Windows it's .lib and .dll respectively, whereas on Linux it's .a and .so respectively. Due to ABI concerns, you also need to make sure that it's compiled with the same compiler and compiler version that you're using, and it also needs to be compiled for the same architecture as your project, 32-bit or 64-bit. Compiler flags present yet another challenge. If the library was compiled with specific optimization flags, exception handling settings, or runtime library options, you need to make sure that your code also matches these settings. When you're sure that you've downloaded the correct pre-built binary, the process for actually integrating it into your project is not simple. That's because when you download a library, it's not just a single file, it's usually a zip file with several things inside. It might contain a debug build as well as a release build and a header file for you to include so that you can actually use the library. So you need to set up a folder for your headers, a folder for your precompiled binaries, and then subfolders for each build. And if you want to build for multiple platforms and architectures, you need subfolders for that as well. And then each binary goes into the correct subfolder. And then you need to watch some 20-minute video on YouTube on how to get your IDE or build system to link the library to your project. And then you realize that this video is for Visual Studio, but you're using Meson, and the library you want to use is using scons, and there's a completely different set of instructions for static libraries versus dynamic libraries, and there's always a lack of documentation for how to integrate it into your build system because it was designed for another build system. It's an absolute nightmare. Also, consider the scenario where you've accidentally downloaded the wrong binary. Maybe it was compiled with a different compiler version or a different architecture or some compiler flags that you're not aware of, or you just linked it incorrectly. You might either get a bunch of incomprehensible errors, or your program will run but you'll get crashes, memory corruption, or undefined behavior at runtime. And then you somehow need to figure out what's wrong without any hints on where to look or what to do. Even if everything does work, if you want to update the library to a newer version in the future, you need to do this all over again manually. And by then you're going to forget how you even got it working the first time around. Or maybe your coworker set it up initially, but then left the company and now you have to figure out how they configured it. In other cases, you might need a 32-bit library, but they only provide a 64-bit version. Or you need a dynamic .dll library for Windows, but all they have is a static .a library for Linux. Or you need it to be compiled with MSVC, but they only have Clang or GCC. In that case, you have to download the code and compile it yourself. And that opens up another Pandora's box of problems. The codebase could be using any given build system: CMake, AutoTools, Premake, Bazel, custom makefiles, scons, Meson, or some weird combination of all of them. And if it happens to be a build system that you're familiar with, it might be a different version from what you have on your system. And then you find out that the library depends on 3 other libraries, which in turn have even more dependencies. You might have to download the binaries or code for those libraries, And those libraries may be different versions of libraries that you're already using in your codebase. So now you're in dependency hell, where the transitive dependencies of the library that you want to use is clashing with the libraries which you're already using. Another annoying issue is when you get a million compiler warnings that aren't even from your own code. They're coming from one of the libraries that you're using. And if you have strict compiler settings enabled to treat warnings as errors, you can't even compile your code until you resolve this. Sometimes you also need to include headers in the right order, otherwise they don't work. That's because macros from one header can scramble up the code in any subsequent headers. You'll get an incomprehensible error like this because you've included windows.h before winsock2.h. The solution is just to change the include order. A beginner would never be able to figure this out on their own, and AI systems like ChatGPT rarely help with issues like this. You just have to pray that somebody else on the internet has had the same issue before and fixed it. Using third-party libraries in C++ is so agonizing that people have developed a practice called header-only libraries to try to make it simpler. In header-only libraries, all of the code in the entire library is put in one single header file so that you can easily just copy and paste it into your project. The inevitable outcome of this is that you end up with these giant files with tens of thousands or hundreds of thousands of lines of code. This increases your compile time significantly because, as we've mentioned before, every CPP file that includes this header recompiles it from scratch. The fact that this paradigm of writing libraries is in such wide use nowadays is a clear-cut sign that something is very wrong with C++'s approach to dependency management. But even header-only libraries don't solve issues pertaining to dependency hell or the macro problems which I mentioned earlier. C++ package managers are an attempt to make things easier, but again, because there's no standard package manager, some people use VC Package, other people use Conan or Hunter. There are pros and cons to each one, and you better pray that the library that you want to use is available to download in the package manager which you've chosen. In the past, when I've used VC Package, it used to download the 32-bit version of each library by default, even though my project was 64-bit. I used to get completely incomprehensible errors during build time, and it took a while to figure out that it was doing this. Newer versions of VC Package have updated this behavior, but the point is that there's always something that goes wrong. Nothing is ever simple in C++. This leads me to a very important point. People often say that C++ will never die, because it has a vast ecosystem of battle-tested tools and libraries. But at some point, you really have to call into question how accessible any of this ecosystem really is, given how exasperating it is to incorporate just about anything into your project. It absolutely sucks how you end up wasting hundreds of hours on dependency management and build system issues, instead of working on your actual project. By the way, I should also mention that some of the most important libraries that you need to use are extremely old and unfortunately unavoidable. If you're programming on Windows, you might need to use the Windows API at some point. The Windows API is a fossil from the 1990s, with decades of accumulated technical debt, backward compatibility hacks, and design decisions from an era when memory was measured in kilobytes. It's the perfect example of how not to design an API, but it's preserved in perpetuity through the requirements of backward compatibility. The variables have inconsistent naming conventions, including weird, outdated Hungarian notation, and many of the types are obfuscated macros. You'll see types like LPCSTR everywhere, which stand for long pointer to const string. Furthermore, dealing with errors is ridiculous. Many Windows API functions return a simple boolean or null and require a separate call to get last error. But it's thread local, so any intervening call to the Windows API might change it before you retrieve the value. Some functions document several different error codes, others have undocumented error codes, and many share the same error codes for different failure modes. And to get a human-readable message, you have to call this function with 7 parameters. The entire API is filled with functions that require obscure flags and magic numbers. The boilerplate to get anything done is absurd. You need like 20 lines of code to read one value from the registry. Take a look at this documentation, which illustrates how to launch a window for opening files. This is meant to be a basic example, and every little thing that you do is like this. It's a complete nightmare. Here's a 1,500-page book for you to read to understand the Windows API. The cognitive burden of C++ is already insane, but adding this to the mix will surely make any beginner programmer's head explode. Perhaps the most important library in C++, however, is the standard library. Standard library code is completely incomprehensible. Any attempt to actually read it and understand it is a fool's errand. Unfortunately, when your program crashes in debug mode, the debugger often takes you deep into the internals of the standard library, instead of pointing to a clear failure in your own source code. But the problem that I really want to highlight with the standard library is that it's missing some very fundamental things that are ubiquitous in the modern digital age. Namely a networking library, HTTP requests, JSON support, modern I/O, modern Unicode support, and command line argument parsing. The Go programming language's standard library completely smokes the C++ standard library in this regard. Its API surfaces are clean, its implementation is human readable, and when something breaks, you can actually understand what went wrong without digging through layers of inscrutable template metaprogramming code. If you want to get anything useful done in C++, you're forced to go on an endless scavenger hunt for third-party libraries, and we've already covered the difficulty and frustration involving in integrating them and managing them. Even the features that do exist in the standard library are surprisingly limited compared to what modern languages have to offer. Standard string is a half-baked solution with no multi-byte character awareness. It's really just a byte string, not a real character string, which means it has no built-in Unicode support. It's also missing basic functionality, like for splitting, joining, and trimming strings, and methods like starts with, ends with, and contains were glaring omissions that weren't added until 2020 and 2023. This is also around the time we finally got standard format, which is a modern way of formatting strings, similar to how it's done in Python. Before standard format, you had to use streams. Standard vector has its own set of issues. The first is that just like string, it's also missing a lot of methods that you'd expect it to have. You instead have to use free functions from the standard library, but free functions are difficult to search for and use in comparison to class methods. In JavaScript, if you want to transform items in an array, you just call .map on the array itself. It's such a nice, simple, intuitive one-liner. But in C++, there's no corresponding equivalent. Instead, you need to call the free function standard transform and insert numbers.begin and numbers.end in a standard back inserter and in a lambda with the ugly lambda syntax. It's really verbose and unsightly, and developers have all kinds of different ways to format it, but it never fits on one line. Modern languages have a way to express this in a single line, and I wish C++ did too. And compared to modern languages, standard vector doesn't have convenient ways for initializing or generating sequential values, or filtering, slicing, reduction, flattening, method chaining, set operations, and a whole bunch of other things. A common theme you might notice is that many of the algorithms in the standard library require you to call .begin and .end in their parameters. I guess the point is to give you flexibility in regards to the range that you want to apply the algorithm on, but like 99% of the time you want to apply the algorithm to the entire vector, not some subset of it. It would have been so much better if there were different overloads of the algorithms, so you could pick if you just want to throw in the whole vector or if you want to get picky with the range. But the former doesn't exist. It's exhausting to write the .begin and .end a million times throughout your entire codebase, especially when you know it's redundant, and all it does is just make the code uglier to read. The other problem is that you could accidentally type .begin on one vector and .end on another, and the compiler won't warn you. You just end up breaking your program. I can't help but laugh at the fact that when you use standard algorithms, you end up with more code than the for loop that they're trying to abstract away. C++ is the only language where the further you go up in the abstraction, the more code you have to write. And to add insult to injury, when you call vector.end, you get an iterator that points to a position after the last element in the vector. This is the back of the vector. Whereas if you call vector.back, you get the last element, which is the end of the vector. Therefore, the end is the back, and the back is the end. If you think that's confusing, then check this out. When you create a vector of string, you get a vector of string. When you create a vector of int, you get a vector of int. But when you create a vector of bool, you don't actually get a vector of bool. The vector has a weird specialization case for bool, where it stores each bool as a bit instead of a byte. So it's not really a vector of bool, it's a kind of dynamic bit set. This saves space, but it doesn't offer all the capabilities and interface of a normal standard container that you'd expect. For example, you can't take the address of a bit within a byte. And when you try to access elements with square brackets, it doesn't return a normal Boolean reference. It returns a proxy object for the bit in question. It also comes at a great performance cost. The whole thing is just so weird and unnecessary. There should have been a separate data structure for this called standard dynamic bit set or standard bit vector. It's such a terrible design mistake. It's also annoying how most of the functions which you'd expect to return a Boolean or an optional actually return an iterator. In JavaScript, there's a method called sum, which you can call on arrays to check if at least one element in the array passes some criteria. To do the same thing in C++, you have to call the free function findIf, and then put numbers.begin and numbers.end followed by your lambda. But this returns an iterator which is not implicitly convertible to a Boolean. So we need to check it against numbers.end. If they're not equal, then the value was found. The code is so verbose, it's exhausting how you have to write the vector name 3 times to get such a commonly used basic algorithm to work. There's no reason why this couldn't have been a simple one-liner like in JavaScript. The last thing I'll say about standard vector is that you need to understand its implementation details to be able to use it correctly. You can't iterate through a vector with iterators while also appending to the vector. That's because when you add an item to the vector, it might run out of capacity, request a larger block of memory on the heap, and then move over all the elements to the new block, effectively invalidating the iterators which are pointing to the old memory location. This also means that any pointers or references that you have to items in the vector will also be invalidated. There's a new ranges library in C++ which lets you perform a lot of the aforementioned algorithms without spamming .begin and .end everywhere, but you still have to use free functions instead of class methods, and deal with iterator return types. And like 99% of real-life codebases still do it the old way. so you need to be well aware of the old techniques to be employable. Either way, I always find myself writing wrappers to make the code look more clean, in cases where I just need a Boolean or optional return type. I also want to touch on unordered map. This is C++'s hash map. It has a very unintuitive API. If you use the brackets operator to check if the map contains a key, you'll end up with an unexpected side effect. If the key is not found, it's added to the map. This behavior is quite odd and not what you'd expect from a hash map if you're coming from a different language. The ergonomics of hash maps in Python and Java are way better. In C++, you have to deal with the awkward iterator pattern that we also used for standard vector. Here's another weird thing about maps. If you try to insert or replace something which already exists in the map, it won't overwrite that value with a new one. It just ignores your insert. This is quite unusual. To fix this, you need to use an if statement to check if your insert failed, or use the new insert or assign method that was introduced in C++ 17. Also, unordered map uses standard pair for map entries, which has members first and second to represent the key and value respectively. This was a terrible decision which sacrifices semantic clarity for implementation convenience. They should have used a dedicated type where the members are actually called key and value respectively. There's so many issues with the standard containers, I can't cover them all. I haven't even talked about how if you're using a container with a custom type, you might run into really weird issues if your type doesn't have a default constructor or copy constructor. Let's talk about the new features. C++ has a lot of new features, and some of them seem pretty awesome at first glance, but when you scratch the surface, you'll notice some glaring omissions in their capabilities. Standard optional and standard expected can't hold references. In Rust, the equivalent types, option and result, don't have this problem. Standard promise in C++ doesn't have a .then function like JavaScript promises. That would be nice to have. It would also be nice if C++ lambdas were as terse as JavaScript lambdas. And a lot of other features like standard span don't have ergonomic slicing, where you can use negative indices to refer to elements from the end of the collection, like in Python where the slice syntax is just so elegant. In contrast, C++ forces you to calculate it manually. The C++ standard library doesn't even use any of the new features, probably because many of the new features aren't compatible with the old features. You'd expect standard library functions to return optional or expected instead of throwing exceptions, but they just don't. You'd also expect to be able to use simple standard library math functions and compile time calculations via const expr, because all the parameters are known at compile time, but you can't because of legacy reasons. And features like smart pointers, standard move, standard variant, and standard visit are so fundamental to the development experience that they should have been built directly into the language instead of being bolted onto the standard library as an afterthought. There's also a list of things in the standard library that you're never supposed to use, but nobody ever tells you that. Seemingly innocent functions like toUpper and toLower and their corresponding wide-char implementations are commonly used to change the case of a string, but they don't properly handle Unicode and other internationalization concerns. You also shouldn't use random because it has poor statistical properties. There are many lists of deprecated features that you can't or shouldn't use anymore, and there's also things which are deprecated and then undeprecated later. Overall, there are a lot of issues with the standard library. But one of the key takeaways is that it's so low level that in order to be productive, you inevitably end up writing your own wrappers and helpers around it to make it useful. But writing good generic wrappers and helpers requires the use of potentially complicated templates, which can have daunting errors if you do something wrong. It's not realistic for beginners to know how to do this. The other option is to use third-party libraries, but as we covered earlier, that can be tricky too. No matter what you choose, if you're a beginner, you're going to have a hard time. And it all just adds to the fatigue of starting a new project. You have to pick which compiler to use, which IDE, which build system tools, which package manager, which style guide. How do you structure your project? Do you have standard library wrappers that you're going to carry over from your last project? Or are you going to use third-party libraries? Which libraries are you going to use? You have to make all these critical infrastructure decisions at the beginning of your project that will haunt you for the rest of its lifetime. Starting a new C++ project is incredibly daunting, and you just can't hit the ground running. Most beginners seem to get stuck on just picking a UI library. Creating a user interface in C++ is another labyrinth that you have to navigate. I can't speak for Linux and Mac OS, but on Windows there are like 10 different official ways to make a UI, each with varying degrees of support for C++. It's hard to figure out which ones are still maintained. Some of them haven't been updated in a long time, and some of them were dead on arrival. Microsoft has developed a habit of pushing out new APIs and unceremoniously abandoning old ones. Some developers write their front end in a different language like C# when they can. But overall, it seems like C++ developers have lost their faith in Microsoft and have opted to jump straight into using cross-platform solutions. Qt is often cited as being the de facto standard for cross-platform applications. It's used in desktop applications like DaVinci Resolve, Maya, Houdini, and VirtualBox. It also supports mobile, embedded, automotive, and IoT devices, but it's not without any issues. People frequently complain about the licensing model being difficult to understand. It uses an outdated version of C++ instead of modern C++. It comes with its own IDE called Qt Creator, and although it's not mandatory, most tutorials seem to use it, so you might struggle to use a different one which you might be more comfortable with. Some devs argue that Qt is bloated, but I can't confirm or deny that. It does have a lot of features, that's for sure. In some respects, that's considered a good thing. Another common gripe amongst developers is that when you use Qt, your code becomes tightly coupled to it. They have their own types like QString that you have to use instead of standard string. But honestly, Qt is probably your best bet for most cross-platform applications. WXWidgets is another cross-platform GUI library, but it's specifically for desktop applications. Its main advantage is that it's a wrapper around each operating system's built-in UI controls, so it provides a native look and feel for your application. But man, some of these libraries are just so damn old. The documentation and the website and the screenshots are so dated, it really doesn't inspire much confidence. There aren't very many new and fresh but also comprehensive C++ libraries being developed, because there's little to no financial incentive for it. That's why we're stuck with these frameworks from the 90s. These days, software developer mindshare has predominantly moved to software as a service products, and by extension, web technologies, because they're faster to build and you can make more money with subscriptions, where you charge for something behind an API, instead of building desktop software, which is typically charged as a one-time purchase. But even desktop software like VS Code, Discord, Slack, Microsoft Teams, Notion, Obsidian, Postman, and Figma are all built with web technologies. I know that most C++ devs would balk at the thought of using a web-based frontend, but web undeniably has the most rich ecosystem for UI. The sheer number of libraries which are available makes it possible to make highly sophisticated, polished interfaces with minimal friction. It's probably the most cost-effective, time-efficient way of creating a stunning cross-platform UI. You can make something in Electron or Atari and have it communicate with a C++ backend. The obvious disadvantage is the bloat and the performance cost, but you might not need the UI to be super performant if you're just clicking some buttons. It really depends on what your application does. The clear advantage is that it's faster to ship, and unlike typical C++ applications, you don't need to wait for your code to recompile when you make a tiny change to the UI. You also have the benefit of a clear separation of concerns between the front end and the back end, and it's easier and cheaper to get web developers to contribute to the UI because they're more abundant than C++ developers who know how to use Qt or WXWidgets. Outside of web technologies, some of the most popular C++ heavy products have custom-built UIs. Adobe products are written in C++ and they use a custom internal Adobe UI framework. Unreal Engine also has a custom-built UI. Blender, which is an open-source 3D computer graphics software tool, has a phenomenal UI, but it's custom-built directly on top of OpenGL, and it's strongly coupled to Blender's codebase. Building a UI from scratch is a Herculean task, but if you're crazy and want to do it anyway, I'd caution you against using OpenGL like Blender did, because at this point in time, it's a legacy graphics API. Vulkan had great potential to be supported on every major operating system, but Apple threw a wrench in that by deciding not to support it on Apple products. And also Vulkan is prohibitively complicated to use, so I wouldn't pick that either. WebGPU is emerging as a strong contender for modern cross-platform graphics development. Don't let the name throw you off. It's not just for the web. It's very well suited for cross-platform desktop applications. It has big corporate backers like Google, Mozilla, Apple, Intel, and Microsoft, and is said to be the next best thing. But you really never know how the future is going to turn out. Picking technologies these days is like picking stocks in the stock market. If you don't want to build something from scratch with a graphics API, there are a lot of other cross-platform UI libraries and frameworks available for C++, but they're all for different niches. IMGUI is fantastic for creating debugging windows for game engines or simulations, but it's not really meant for user-facing UIs. Juice is for audio applications and audio plugins. GTK has first-class support for Linux, which is good for Linux, but they don't seem too keen on fixing bugs that occur on Windows. FLTK is another option, but it looks really outdated. There are many others too, but I didn't include them because honestly, I'm never impressed with the applications that are built with them. A common theme I see is that new GUI libraries for C++ advertise themselves as being modern, but this ends up being unintentionally deceptive because what they really mean is that the library is written in modern C++, not that the UI will look modern. In other words, modern C++ does not equal a modern-looking UI. But no matter which library you choose, you're inevitably going to have to deal with errors.
Error messages in C++ are excruciating. The compiler will vomit 1,000 lines of impenetrable garbage simply because you misplaced a single character. Errors are a typhoon of angle brackets, semicolons, underscores, and leaky implementation details from the standard library that are enough to give any beginner a heart attack. Not only are they exceedingly verbose and utterly incomprehensible, they're often completely unrelated to the issue at hand. If you're refactoring code, you'll just have to come to accept the fact that the compiler is going to spit out 500,000 lines of errors if you don't do everything perfectly right the first time. And I hate how Visual Studio doesn't let you select the error that comes up in the tooltip to copy and paste it, so you have to type it all out manually in Google to see what it means. Templates, by the way, make errors a million times worse. Templates are how you do generic programming in C++. Let's say I have a function that takes in an int and prints it to the console. If I wanted to make one for double and string and float, I'd have to write out 3 more functions. But with templates, you can write a single function and instruct the compiler to automatically generate all the others for you. They're like blueprints for generating code. This is one of the key advantages of C++ over C. In C, you need to re-implement each data structure for each type you want to use it with, whereas in C++, you can generate them with templates. Templates are incredibly powerful in ways that I can't even begin to explain, but there are a number of problems. First of all, they can get extremely complicated. There's an 800-page textbook solely on C++ templates. Second of all is that they produce enormously long cryptic error messages that are incredibly difficult to decipher. These errors frequently take up an excessive amount of horizontal space. I can't get them to fit on my screen, even on my 4K monitor. I finally see the appeal of those ultra-wide monitors. The distance between your eyes needs to be at least 20 centimeters so you can read these goddamn errors efficiently. And don't waste your time changing the settings to wrap the text over to the next line. It'll make the errors even more incomprehensible to read than they already are. Oftentimes, I end up using much smaller font than I'm comfortable with to try to fit as much of the error as I can on the screen. But this inevitably leads to me squinting my eyes or moving my head forward in an unergonomic position to read the tiny text. It's no wonder that C++ developers need glasses and have forward head posture and RSI in their neck. Another problem is that template-heavy code significantly increases build times, since the compiler needs to generate specialized code for each template instantiation. This, of course, can lead to an increase in binary size. There are also rules around templates like how generally they must be implemented in header files. In other words, you can't separate the interface and the implementation like how you can with regular functions. Also, historically, IDEs have had very poor tooling support for templates. IntelliSense often breaks, and static analysis tools often struggle with complex template code, providing less helpful suggestions or completions. And stepping through templated code in a debugger can be confusing, since the debugger has to navigate through instantiated template code. Templates are also used for template metaprogramming. This is one of the most powerful but also challenging aspects of C++. It's a technique used to perform computations at compile time rather than runtime, by acting as a sort of functional programming language within C++ that executes during compilation. All the problems with templates apply doubly so to template metaprogramming. The learning curve is incredibly steep because the recursive style which it is written in is fundamentally different from normal imperative C++. Not to mention, its syntax is even more verbose and obscure than normal C++. The code is often so complex that it becomes difficult for even experienced developers to maintain and modify. And it's a debugging nightmare because it executes at compile time, so traditional debugging techniques don't work. And of course, just like raw templates, it can dramatically slow down compilation times. One really big flaw with templates and template metaprogramming in general is that they don't have a built-in direct way to limit which types are allowed to be used with the template. So for example, maybe you have a template that's only supposed to be used for numeric types. We need a way to limit the user from using it with non-numeric types. To solve this dilemma, developers came up with a technique called SFIN-A, which stands for Substitution Failure is Not an Error. This is probably the most poorly named thing in the whole language. It's basically just a pattern for writing templates in a way that should only work for types that have some given property. A better name would have been template type constraints or something. Nevertheless, it's extremely verbose, it creates unreadable nested template expressions, it uses specialized template metaprogramming tricks that are hard to understand, the errors are cryptic, and it requires significant template metaprogramming knowledge to write correctly. Perhaps the biggest flaw, however, in metaprogramming in C++ is that the metaprogramming language is wholly different from the programming language itself. In contrast, Zig uses the same programming language for regular programming as it does for its metaprogramming system, which is called comtime. In other words, if you can write regular Zig, it's trivial to write compile-time Zig code because it's the same language. It kinda makes you wonder who even designed template metaprogramming in C++ and why was it designed this way? And that's the kicker. Nobody designed it. Template metaprogramming was discovered. Originally, templates were introduced as a mechanism for generic programming, allowing you to write code that works with any data type. But then, developers discovered that templates were accidentally Turing-complete, meaning that it could be used for complex compile-time computations, something not originally intended in their design. The first notable example was in 1994, when Erwin Unruh demonstrated that you could use them to print prime numbers at compile time instead of runtime. Since then, programmers have continued to exploit this accident to perform compile-time computations, and C++ codebases are now filled to the brim with abstruse template garbage to solve problems that could have been much more elegantly solved in other pre-existing solutions such as Lisp macros. C++ tried to roll with template metaprogramming and added even more features on top of it like partial template specialization, which I won't get into. It's crazy to think about how C++ is so complex that you have these extremely consequential, accidentally emergent properties that are born out of its complexity. As of the past few years, C++ has been trying to do the same thing as Zig's comtime with their own keywords const expr, const eval, and const init. This lets you use regular C++ code to do some of the things that template metaprogramming can do, but it's fairly new with a lot of edge cases and rules, and most of the industry hasn't caught up to it yet, so you still need to know the old way of doing it in order to be employable. The advantage of Zig is that it simplifies everything by designing comtime up front, rather than incrementally implementing it with ad hoc rules over a period of many years like C++. There's also a new feature called C++ Concepts, which is meant to replace Spin and help templates provide more helpful error messages, but this is a terrible name because it's hard to Google for. The term C++ Concepts, which refers to this specific C++ feature for template type constraints, can easily be conflated with the English word concepts, which refers to ideas or just general programming knowledge. This ambiguity makes it frustrating to find relevant search results. Templates aside, there are a lot of quality of life things that just suck. Here are some things that annoy me about writing C++ in Visual Studio, and I'm sure that other IDEs also have many of these problems. Number 1. When you make a new project, the default settings are completely off from what you'd expect. It puts you on an outdated version of C++ from like 10 years ago. The default folder structure is bizarre. The optimization settings are suboptimal. You have to go in and change so many things almost immediately, but there's so many options it's hard to remember what to change. Number 2. There's so many windows, tools, configurations, settings, panes, and panels everywhere that sometimes C++ IDEs feel like a flight deck of an aircraft with a million toggles. If you accidentally touch something, you'll never figure out what the hell you just clicked or activated. Usually we can use source control to undo the changes, but sometimes certain things just happen to sneak in. One time I spent a few days trying to figure out why my code was throwing an error that I've never seen before, seemingly out of the blue. I checked online, but I couldn't find anything. I studied the code like a madman, literally spinning my wheels for days, until eventually, by some miracle, figured out that somebody had accidentally opened the exception settings pane, which I didn't even know existed at the time, and they accidentally toggled on an inessential debug exception that was off by default. I think it was something to do with some external driver code that was not part of our own codebase. The solution was simply to toggle it off. That was it. There were no issues with the code. It was just this one little checkbox. I wasted days on this. It's one of those bugs that you just never forget. Number 3. I consistently have really weird formatting issues. Here's an example which I regularly have with switch statements, where my cursor goes like way into the right-hand side for some reason. Copying and pasting code also tends to screw up the formatting, especially when using lambdas. Number 4. I already mentioned this earlier, but it's worth mentioning again. Autocomplete sucks because the language's header-based inclusion model indiscriminately injects vast numbers of symbols into your code. Number 5. IntelliSense and code navigation starts to fail as your project gets larger, and even on smaller projects, macros and templates can confuse IntelliSense. Number 6. Tools like static analyzers produce false positives, and can be much more resource-intensive than analyzers for other languages. This is probably because C++ is just so complicated. Number 7. AI tools aren't very good at writing C++ code or helping you with C++-related problems. I'm not against AI personally. I think it works wonderfully for web technologies, but it leaves a lot left to be desired for C++. Number 8. There aren't many features for refactoring. If you rename a file name, you have to manually update the include guard, and then you have to use the clunky Ctrl+F to find all the places where it's included to update the name. And if you care about things like alphabetical order, you have to do that yourself too. The refactoring features that do exist are very limited and unreliable. Number 9. Code snippets in Visual Studio are broken. Given the verbosity of C++, I'd really like to have working code snippets, but half my snippets keep breaking. I don't know what's going on, but I just gave up on using them. Number 10. I often add a comment to closed curly braces to signify the context. There should be an option to make the IDE do this for you, but there isn't. Number 11. There's a feature in Visual Studio to show inline hints if you hit Alt F1. It's basically useless because the types are so long that they don't fit in the hint, and you'd expect that if you hover over it with a mouse, that it would show you the full type in a tooltip, but it doesn't. Number 12. You can't select errors in tooltips to copy and paste them. We already covered this earlier. Number 13. I had an issue in the past where if I changed the extension of a file from .hpp to .h, Visual Studio completely spazzes out with some useless and irrelevant error message that forces me to go into the actual VCX project file and meddle with the internals of the project setup to get my project working again. It took me many hours to figure out that changing the extension name was the cause of this issue. Number 14. Historically, there was no easy way to set the default file encoding, but finally this year they added a way to do that. Number 15. When you want to include a header file, you need to manually type it out at the top of the file. I've been doing some JavaScript lately, and it's such a breath of fresh air to be able to hit tab and have the library automatically imported at the top. This is a feature which I genuinely miss. It actually makes writing code so much more fun. Number 16. C++ is a new feature called designated initializers, which allows you to initialize members of a struct explicitly by name. The designators must be used in the same order as the members are declared. Sadly, my IDE doesn't recommend them in that order in the autocomplete. It's annoying to have to travel to the struct definition to see the order of the members, and then jump back and forth to make sure that the order is correct. IDE problems aside, there are a lot of quality of life issues related to the language itself. The first one that comes to mind is that you can't use a function unless it's declared above the function which you are calling it from. I miss writing in languages where the order in which you write functions doesn't impose limitations on which functions can be called. C++ also doesn't have struct update syntax, which would allow you to create a new struct by modifying specific fields of an existing one, while keeping the rest unchanged. And there's no concise, idiomatic mechanism to enforce full member initialization in aggregate types. While constructors technically solve this, it's not idiomatic to use them on structs, because it undermines the semantics and ergonomics that make struct declarations attractive in the first place. Alternatives such as the builder pattern or custom member wrappers like force init are verbose and require too much boilerplate. The absence of a first-class language facility for mandatory initialization at the field level leads to subtle bugs and forces developers to choose between safety and simplicity. Another egregious ergonomic failure is standard visit, which is the C++ way of doing Rust's pattern matching, but it's inferior in almost every way. Firstly, to get it working similarly to Rust, you have to add this template magic boilerplate, which you can see recommended here in CPP reference. But the boilerplate is different depending on which C++ version you're on, and many developers don't like how the value goes in as the last parameter instead of the first. If you're pattern matching, it makes more sense to have the value at the top than the bottom. To really get it working well, you need to add even more template magic boilerplate. And because it's also template heavy, the compilation times and binary bloat can be considerable. Additionally, IDEs like Visual Studio won't autocomplete the different arms of the visit, so you need to find the variant definition to check the types and then switch back and forth to reference them while you type them out manually. In contrast, Rust has excellent ergonomics and autocomplete support for pattern matching. When you've tried pattern matching in Rust, you'll never want to go back to using standard visit in C++ ever again. Serialization in C++ is also terrible, because it doesn't have reflection like Java, and there's no standard serialization framework. As a result, developers are forced to resort to brittle and verbose boilerplate, rely on intrusive macro-based libraries, or adopt external tools that impose unnatural constraints on design. Even seemingly simple tasks like converting a struct to JSON requires disproportionate effort or using some hacky third-party library. The core issue is the absence of introspective access to an object structure. In C++, type information is largely erased at compile time, and there's no facility to generically enumerate members, capture type metadata, or traverse object graphs without explicit and often repetitive code. This not only inhibits serialization but also impairs related concerns, such as configuration loading, remote procedure calls, data binding, and UI reflection. If you want to do something simple like converting an enum value to a string so you can output it to the debug console, you can't do this natively in C++, and there's no simple way to create an abstraction for this. You need to laboriously write code for every single enum that you want to be able to log, and if somebody updates the enum, you can't forget to update your serialization code. There are some GitHub libraries out there like Magic Enum that offers static reflection for enums, but it doesn't use C++ language features. It uses clever hacks based on compiler extensions. Developers are cautious about using hacks like this in their codebase, so you can't use them in any project that you want. Other solutions include writing Python scripts to generate the enum serialization code, but adding another language to your codebase complicates the build system even more. Allegedly, reflection will be added in C++ 26, but like all things with C++, it's arriving way too late to the game, and it's likely going to be bolted on with verbose and unintuitive syntax. Furthermore, it's going to take the industry like 10 years to catch up to that version, so you're stuck doing this the old way for the foreseeable future. C++ also has bad defaults for many of its features and behaviors. By default, variables are immutable. To make them constant, you need to use the keyword const, which inevitably ends up being spammed everywhere all across any given C++ codebase. They should be const by default, and mutability should be opt-in, with a special keyword like mutable or mute like what you see in Rust. The code would look cleaner and be less bug-prone. The other problem with variables is that they initialize with garbage values. If you make an int but don't assign it to anything, you might expect the value to be set to 0 by default. But instead you end up with whatever was in memory at the time of the initialization. So the value of int could be anything, and it can lead to very subtle but catastrophic bugs in your program. Variables should have better default values. Numeric types should default to 0.
and pointers should default to null pointer. This aligns with the principle of least surprise, and eliminates a vast class of latent bugs caused by uninitialized memory reads. For those who want more performance, there should be a keyword to leave the variable uninitialized. Constructors also have an issue with bad defaults. Let's say I create a class animal with one parameter in the constructor, the age of the animal. Now let's make an animal. I can do that by setting animal cat to animal with an age of 5. Everything works as expected, but assigning it to just the number 5 also works. That's because C++ implicitly converts 5 to animal and passes 5 into the constructor. This is the source of many bugs where programmers mistakenly pass one type around where another type is expected, and the compiler silently accepts it. To fix this, you have to use the explicit keyword on the constructor. It would be much more sensible for constructors to be explicit by default, and have an opt-in implicit keyword to do the opposite instead. Classes have a bunch of bad default behavior. Destructors are non-virtual by default. This causes memory leaks when derived objects are deleted through base pointers. It's a very common mistake to forget marking destructors as virtual. Inheritance is weird too. When you inherit something via class, it does private inheritance by default. Some developers argue that it should be public inheritance by default, just like basically every other language. And the override specifier is optional by default, but it should be mandatory. There's also a keyword this, which gives you a pointer to the current instance of the class. The default behavior should be to give you a reference. Switch statements also have a bad default. You have to add a break in each case, otherwise it'll fall through. It's easy to forget to put in a break. It should be break by default. Even data structures in the standard library have plenty of bad defaults. Standard vector has 2 different ways of accessing an element. The most common way is to use square brackets. This has no bounds checking, so if the index is out of bounds, it results in undefined behavior, which can lead to memory corruption, crashes in unexpected places, or security vulnerabilities. This is what most developers use. It seems like most devs don't even realize that there is a safer alternative way to do this, with the @member function, which does have bounds checking. In this case, if the index is out of bounds, you get sensible behavior. It throws a standard out-of-range exception. The default behavior should be in reverse. Access via square brackets, which most people use, should have bounds checking by default, whereas the method call should be without bounds checking, so that using it in performance-critical scenarios is opt-in. This would prevent so many security issues and headaches all across the world. This type of problem is pervasive all throughout the standard library. The default behavior is always dangerous, and the safe behavior is hidden in some obscure method. If you're smart, you'll almost always use the safe access patterns. The unsafe access patterns are for performance-critical scenarios. C++ also has something called attributes, which are for annotating code with additional information for the compiler to use. The no-discard attribute helps prevent bugs by warning when function return values are ignored. For instance, the member function empty in vectors returns a Boolean value, indicating emptiness, but developers might mistake it for a clearing function and ignore its return value. No-discard issues a compiler warning for them to acknowledge the return value. It's a great feature, but it should be the default behavior for every function that returns a value, and there should be a discardable attribute instead, for the odd case where you don't want this behavior. The NIM programming language does this really well. In NIM, if you ignore a return value, you get a compiler error, unless you explicitly use the keyword discard. The current state of affairs in C++ makes new features like standard expected tedious to use correctly, because you need to spam all standard expected return types as no discard to have robust idiomatic code. There are other problems as well when it comes to bad defaults. C++ copies by default. It probably should be moved by default like Rust. More on this later. C++ also has a keyword noExcept for indicating that a function won't throw an exception. Some developers think that everything should be noExcept by default. Java has the opposite, where you indicate that a function does throw instead of that it doesn't. Additionally, some developers believe that exceptions should be opt-in by default instead of opt-out, and everything should use standard expected by default instead of exceptions. Other developers argue that everything should be const expert by default when possible. Perhaps the most important default would be that every header should be included only once by default, so that you don't need to incessantly write header guard boilerplate everywhere. Even the new modules feature has bad defaults. You have to write module at the top of the file to get it recognized as a module. It's very weird. I'd prefer not to do that. The most ironic thing about C++ is that despite being incredibly verbose, a lot of very important things are completely invisible in the language. Copying is one example of this. In high-performance programming, understanding when and where data is copied is critical. Unnecessary copies can cause performance degradation, excessive memory usage, and unpredictable behavior. However, in C++, copies are often invisible, and determining when they occur requires deep knowledge of the language. An innocent-looking equal sign could be copying over 100 megabytes of memory, or triggering a database query, and function calls can trigger multiple hidden copies as values move through parameters and return values.
Additionally, the difference between deep and shallow copying isn't obvious from syntax alone. Consider this simple assignment. You can't tell if Object 2 now shares internal resources with Object 1, or if Object 2 received its own independent copy of all the data. The behavior depends entirely on how the copy constructor or assignment operator is implemented for the class, which is not visible at the assignment site. The fact that such fundamentally different operations share the same syntax makes C++ code hard to reason about without a deep knowledge of every class's implementation details. And with all the constructors in C++, it can be hard to figure out if a line of code is invoking a default constructor, a copy constructor, a move constructor, or conversion constructor, or something else. Sometimes you end up with multiple constructors being called in succession, and it all happens behind the scenes without you being aware of it. In contrast, other languages have recognized this issue and have explicit syntax or methods for copies, like clone and copy. It's incredibly ironic how in C++, the amount of code that you write is inversely proportional to how much the operation actually matters. If you want to write a trivial operation, you need to write 100 lines of template metaprogramming code. On the other hand, a little equal sign is quadrupling your memory usage. Implicit conversions are another particularly insidious form of invisible behavior in C++. They introduce inefficiencies, lead to precision loss, and create subtle bugs. Take a look at the following code. Here we have a function that accepts a string, and here we call that function. It seems pretty straightforward, but it isn't. The function which you think is being called isn't being called, because somewhere else in your codebase there is another function with the exact same name that accepts a boolean, and unintuitively, the one with the boolean parameter is being called at runtime, even though we're not calling it with a boolean type. That's because the string literal is implicitly being converted to a pointer to const char, which is then converted to a boolean, so it calls the function with the boolean parameter. This is absolutely appalling. Here's another example. C++ has no problem letting you return an integer when the return value is meant to be a string. This code demonstrates a classic truncation bug where we have a 64-bit customer ID, which could be from a database or API. We accidentally store it in a 32-bit variable, the high-order bits are silently truncated, and we end up with a completely different ID. This kind of bug is particularly insidious because the program compiles without warnings, unless you enable strict warnings. It runs without crashing, it silently corrupts data, and in a real application, this could lead to accessing the wrong customer's data, making changes to the wrong records, or sending sensitive information to the wrong person. Such bugs become even more dangerous in systems handling financial transactions, medical records, or security-critical operations. There are a whole bunch of footguns around implicit conversions in C++ that you have to know, and even if you memorize them all, they can still often catch you by surprise when they happen. In C++, copies and implicit conversions aren't the only examples of invisible behavior. Benign-looking operators can execute any arbitrary code due to operator overloading, and exception handling creates invisible paths through your code that can obscure the control flow. C++ also doesn't have call site reference syntax. When you're calling a function in C++, there's no indication at the call site that you're passing by value, reference, or non-const reference, so it's not obvious if the value will be modified. You have to go to the signature of the function to verify this. In Rust, you can see all this information at the call site. This feature makes the code easier to understand, and it's sorely missing in C++. And this is perhaps the cruelest thing about C++. It's gratuitously verbose about mundane operations and conspicuously silent about expensive operations. Developers often argue that C++ is verbose because high-performance programming is verbose. It stands to reason that if you want to write highly performant code, verbosity is the natural consequence of expressing fine-grained surgical intent to the hardware. But C++ isn't verbose for this reason. It's verbose because of bad design decisions and historical baggage, like code duplication between header and CPP files, namespace prefixes, template syntax, verbose language features like static cast, idiosyncratic and pretentious naming conventions like standard unordered map and standard monostate, bad defaults which require you to spam const, explicit, no discard, and no except everywhere, poor standard library design which requires you to spam begin and end everywhere, and features that should be integrated natively into the language are bolted on as an afterthought in the standard library instead, like standard move, variant, and visit. There's also a lot of other unnecessary code duplication design decisions like const and non-const method pairs that execute the exact same piece of code. There should be a way to write this as only one method instead of two. The point is that it's not verbose because it's close to the hardware, it's verbose to satisfy legacy constraints, backwards compatibility, and poor design decisions. You spend more time managing the language than managing the hardware. It absolutely could have been a beautiful, clean, clear, succinct language. I strongly empathize with beginners who naively write using namespace std in an effort to try to clean up the language and make sense of it all. Experienced developers on internet forums routinely belittle beginners by telling them that they're stupid for doing this, and then they start parroting technical reasons like namespace pollution and name clashing as to why this is a problem. But the real answer as to why you shouldn't be using namespace std is because the language sucks. And any effort that you spend as a user of a language to clean it up or try to fix it is an exercise in futility. That being said, when it comes to things that are actually important, there's barely any verbosity in the language at all. Copies should be more explicit. Implicit conversions should be explicit. Functions don't tell you what exceptions they throw like in Java. It doesn't have call-side reference syntax like Rust. And there's so many cryptic abbreviations that should have just been written in plain English. You could say the same thing about the errors too. The compile time errors are disgustingly verbose, but the runtime errors won't even print the stack trace. When it comes to verbosity in the language, C++ is a total farce that has it all completely backwards. Anyways, let's talk about some of the features of C++. I'm going to start with operator overloading. Operators are symbols that perform operations on variables and values. When you add two numbers together, the plus sign is an operator. But what if you have a custom type? Regular addition isn't going to work. Operator overloading means that you can make it work. You can implement your own logic for how the plus symbol should operate on your objects. Other languages like Java don't support this, and for good reason. It's a controversial feature. Let's say you have a vector, not a standard vector, but a physics vector with a direction and magnitude. If you were to overload the multiplication operator, it wouldn't be clear if this is going to perform a dot product or cross product. If you just used a normal function instead, you'd know what it was by looking at the name. I've also seen operator overloading used in very weird ways. Standard file system path from the standard library overloads the / to represent the path separator. A lot of developers find this very jarring, because the / is typically thought of as being used for division. But in this case, it's being used for concatenation, which is an operation that is more conventionally associated with the addition symbol. In other words, it's using the division symbol to add things together. Another weird thing you can do is overload the ampersand symbol operator, which is meant to give you the address of the object. You can overload it and just return a random number. Now anybody who uses the ampersand symbol thinks that they're getting the memory address of the object, but they're just getting the number 2 every time. And if they try to dereference it, they'll probably get a segmentation fault or something. So if you want the real address of an object without any tricks, you shouldn't use the ampersand operator. Instead, use the function standard address of. But then what was even the point of the address operator to begin with? To add insult to injury, classes in the standard library, which you would expect to overload the address operator, like standard reference wrapper, don't even overload it. The entire language is filled to the brim with inconsistencies, paradoxes, and solutions to the problems which it created itself. And by the way, don't get standard address of mixed up with standard to address. It looks similar and it's easy to get them mixed up, but it's actually completely different. The insanity doesn't end here though. You can also override the new keyword, delete keyword, and the comma operator. But that's enough talk about operator overloading. Let's briefly cover ownership and move semantics. Ownership is about which piece of code is responsible for managing a resource, and move semantics allows for the efficient transfer of resources from one object to another without expensive copy operations. To perform a move, you use the function standard move from the standard library. But like all things in C++, standard move is a misnomer. It doesn't actually move anything. It just casts the specified value to an unnamed temporary, allowing it to bind to an R-value reference. It should have been called standard R-value cast or something like that. And if you don't know what an R-value is, just wait till you learn about L values, GL values, PR values, and X values. Furthermore, there are situations where standard move just silently makes a copy, and other situations where you don't want to use standard move, but rather standard move if no except instead. And there's also another standard move in the standard library. So don't get the move from the utility header, which is the one we use for move semantics but it doesn't actually move anything, mixed up with the one from the algorithm header, which actually does move things. It's all pretty simple stuff, man. If you're still confused, I'm sure that this 300-page textbook on move semantics will clear things up for you. Or you can just give up and learn Rust instead. The documentation for move semantics in Rust is 1 page. One of the things I wanted to do in this video is show you a list of miscellaneous quirks and footguns in the language. But the problem is that my list became way too long. I don't want to spend 10 hours on this. Maybe I'll post them on my GitHub or on X, so follow me there if you're interested. For now, I'm just going to cover a few of them in no particular order. Number 1 is about initialization quirks. Both aggregate initialization and initializer lists use curly braces, and the official definition of aggregate initialization has changed in nearly every version of C++ since C++ 11. The same line of code will return a different type depending on which version of C++ you're using, and whether you include or omit an equal sign can completely change the type of the thing which you're initializing. 2. C++ has a unique way of assigning constructor arguments to member variables. In contrast to Java, where this assignment happens in the body of the constructor, C++ uses member initializer lists that appear between the constructor's parameter list and body. But there's a weird caveat. Members aren't initialized in the order which they appear in the member initializer list. They're initialized in the order which they're declared in the class definition. If you initialize the variables in the wrong order, and some variables depend on other variables, you may end up using an uninitialized variable,
and that can lead to undefined behavior, which you definitely want to avoid. 3. The order in which you define members in a struct or class affects the size of the struct or class, because padding may be inserted by the compiler to satisfy memory alignment requirements. To minimize the memory footprint, make sure to put the biggest data types first. 4. There's no real way to know what order static variables are initialized across different CPP files. So if you have one static object that depends on another one in a different translation unit, there's no guarantee that they'll be initialized in the correct order. This is a notorious issue called the static initialization order fiasco, and it can lead to subtle, non-deterministic bugs that are difficult to detect and even harder to diagnose. 5. The standard library has a function called standard launder, which is for laundering memory. Just make sure you don't use it with standard gem money. We're here to write fast code, guys, not break the law. 6. Make sure to always check what comes after the closing brace of a lambda. If there are parentheses, it means that the lambda is being executed in place. This is easy to miss, so try to use standard invoke when you can to make it more explicit. 7. C++ allows multiple inheritance, which means that you can run into the diamond problem. Be mindful of that.
8. If you assign a derived class object to an object of its base class, the derived class object's members and behavior will be sliced off. Only the base class portion is retained. This is called object slicing, and it can lead to loss of polymorphic behavior, data loss, and silent failure.
9. Never prefix your variables with an underscore, because that's reserved for the implementation details of the standard library and the compiler. 10. In C++, anything can be thrown as an exception. You can throw a number or a string if you want, but don't actually do this. And if you're writing custom exceptions, it's best practice to make them inherit from standard exception. So try not to forget that. I'm gonna stop here. I could go on forever. This is barely the tip of the iceberg, and I still haven't even covered variadic templates, parameter pack expansion, fold operations, perfect forwarding, the spaceship operator, type erasure, the most vexing parse, the decal type specifier, and coroutines. You can look into these yourself. Or you can just give up and learn Python.
As you can see, C++ is a monster of a language. It's a freak show. It's a clown car of features. Most compilers haven't even fully implemented C++ 20 yet, and the standard committee has nearly finalized C++ 26. Additionally, some features like standard memory order consume are so complicated, the compiler developers have given up on implementing them. And online, developers incessantly argue about little technical details, like if prefix increment is faster than postfix increment. Apparently it is. But even though C++ has a lot of features and quirks, it's not any single one which makes it difficult. It's the combination of them that makes it difficult. When you learn about new features and tutorials, they're typically presented in isolation, through contrived examples whose artificial simplicity masks the true nature of production-grade C++ code. In real-life code bases, it's not uncommon to encounter a single block of code which has smart pointers and templates and lambdas with coroutines and macros and compiler extensions, with some of it running at compile time versus some of it running at runtime. It's the combination of all these features that makes C++ hard to read and reason about, and maintain. And learning a language isn't just about memorizing its features. It's also about learning the idioms of the language. Idioms are language-specific design patterns. C++ has a lot of idioms, like the copy and swap idiom, the attorney-client idiom, the passkey idiom, the policy-based design idiom. Even templates have their own idioms, like the tag dispatching idiom. Here's an ever-changing list of 100 C++ idioms. And new features like reflection are probably going to add even more idioms to the list. C++ is also used in a lot of highly specialized fields. That means that knowing how to use the language is not enough. You also need deep domain-specific knowledge. If you want to work in high-frequency trading, you'll need strong math skills. If you're working on computer vision systems, you'll need to understand AI. If you're building simulations, you may need a solid grasp of physics. If you're working on game engines, you'll need to understand graphics programming, which is an entire subfield of its own. And that's why C++ is so tricky. The industries that demand C++ are precisely those where the cognitive load is already at its limit from domain complexity alone. The language doesn't exist in isolation. You have to be an expert in a field that's challenging in its own right. Not to mention the added stress of using such a flawed, fragile, memory-unsafe language in critical systems like medical devices, where if you write even one incorrect line of code in a million-line codebase, you could end up putting people's lives in jeopardy. This leads me to the topic of memory safety. C++ is not memory safe. Memory safety refers to a broad category of issues related to how a program manages memory. When we say that C++ is memory unsafe, it means that the language lets programmers write code that can lead to various issues such as memory-related errors, security vulnerabilities, or unpredictable behavior. For example, dangling pointers, memory leaks, use after free, double free, use after move, buffer overflows, uninitialized memory access, null pointer dereference, mismatched allocation and deallocation, iterator invalidation, lifetime issues with references, and pointer arithmetic errors. These are like hidden traps and ticking time bombs in your codebase. They may corrupt data, crash systems, and create catastrophic security vulnerabilities. And they can be incredibly difficult to debug because the problems which manifest are very far removed from the actual cause, both in terms of code location and execution time. And they can be hard to reproduce because they only occur under specific conditions. Memory corruption can also damage the very information debuggers need to analyze the problem. And even specialized memory debugging tools may miss certain classes of errors or introduce runtime behavior changes that mask the original problem. And memory issues can interact with other parts of the program in complex ways, creating a tangled web of cause and effect. And I haven't even touched on thread safety issues like race conditions and deadlocks. Modern C++ practices like using smart pointers help mitigate some of these issues, but they don't even come close to getting rid of them all. There's a lot of discussion about how to fix these memory safety issues. I've seen people at conferences argue that unsafe code is the result of programmer negligence, poor discipline, or inadequate education. But the only people who benefit from this sort of narrative are consultants and people who sell textbooks and courses on C++ to profit from the language's complexity. The issue is clearly not a skill issue or a culture issue. It's a technology issue. Even the best engineers at FAANG companies make catastrophic mistakes when writing C++. Some data from Google and Microsoft shows that up to 70% of security vulnerabilities are related to memory safety. There have been statements issued by the NSA, CISA, FBI, White House, and European Union on the national security concerns of using memory-unsafe languages like C++. Businesses are being pressured to switch over to memory-safe alternatives like Rust. Prominent figures in the tech space have echoed similar sentiments. AWS, Azure, and Cloudflare are now building cloud infrastructure in Rust. Google has started using Rust in Android, and Microsoft has started using Rust in Windows. Even the creator of Linux, who has been fairly outspoken about his dislike for C++, has allowed Rust into the Linux kernel. This is very telling. Adjacent to the topic of memory safety is this thing called undefined behavior. This is a critical topic that every C++ developer needs to understand to write safe code. The basic gist of undefined behavior is that in contrast to languages like Java, where if you do something wrong you get an exception, the C++ standard doesn't actually specify what should happen. It could crash the program, memory can get corrupted, code can run in unpredictable ways. Now you might think, if undefined behavior is undefined, why not just define it? And the answer is performance. If you try to access an index which is out of bounds in Java, Java does a check under the hood to see if the index is out of bounds, and then it throws an exception if necessary. All of this extra logic incurs a performance penalty. That's why C++ omits it and substitutes it with nothing. If you access an out-of-bounds index in C++, the standard doesn't specify that the language should protect you from doing this. It doesn't even specify what should happen. You could end up corrupting memory in some other part of your program, or you could get a segmentation fault or God knows what else. It's incumbent on you to know not to do this. Undefined behavior is deliberately undefined to maximize performance. It allows the compiler to make optimizations that would otherwise not be possible. The problem is that it can lead to a variety of awful bugs in your program. And this is the Faustian bargain of C++. You get raw speed and low-level control, but in exchange, you must live with a constant, silent threat of annihilation. This prioritization of performance over memory safety is somewhat ironic, because there's no slower program than one that stops running. That being said, the list of things which are considered to be undefined behavior is staggering. Moving on to error handling, this is another contentious subject with no consensus on the best approach. Many developers advocate for exceptions because of their ability to automatically propagate errors up the call stack and their potential to separate error handling logic from the normal program flow. But there are some disadvantages. They introduce performance overhead, both in terms of runtime behavior and binary size, and can complicate control flow in ways that make the code hard to reason about, and potentially hinder compiler optimizations. The extent to which these penalties matter in practice is widely debated, often depending on application domain, performance constraints, and coding style. Complicating matters further is the issue of ABI boundaries. Throwing exceptions across shared library boundaries can result in unexpected problems, including crashes or memory corruption, especially when there are mismatching compilers or if the standard libraries differ between the components involved. In response to these concerns, some developers prefer the new standard expected, introduced in C++23. It's similar to the results type in Rust. Unlike exceptions, standard expected enforces explicit handling at the call site, making control flow and error paths more visible and deterministic at the cost of additional syntactic overhead. At this point, you probably won't be surprised to learn that C++ doesn't have a standard way of writing tests. Just like all other aspects of C++, the community is fragmented. Some codebases use Google Test, some use Catch2, others use Boost, and occasionally you'll stumble upon a homegrown Frankenstein of macros and hacks. It's honestly flabbergasting to see all the different hacks that developers use to test private member functions. There's simply no consensus on how to do this, or whether you should even do it at all.
In programming languages that have reflection like Java, you have the flexibility to reach into the guts of an object if you really need to. But in C++, I've seen people use preprocessor macros to turn the keyword private into public. But doing this will make everything public, even the things you didn't intend to. There are other ways to use preprocessor macros too, but they just end up polluting your code. Other tricks I've seen include changing private functions to protected, and then having the test class inherit the class to be tested. But using inheritance to circumvent encapsulation for the sake of testing is not what inheritance was designed for. Furthermore, I've seen codebases make everything public so that it can all be accessed, but this breaks encapsulation. Or you can make your test class a friend class of the class which you're testing. But now classes need to be aware of the classes which are being used to test them. This is poor design because it entangles the implementation details with the test infrastructure. The only sensible solution is to refactor out the implementation details into a free function and test the free function instead. So your class is basically just a thin wrapper around public data types and free functions. This is a very atypical way of writing OOP that makes some developers uncomfortable. It would be easier if there was a standard way of doing this so that developers don't need to come up with all these coding gymnastics. Additionally, the process of incorporating a third-party testing framework is another headache. Beginners are often surprised to find out that if your project compiles down to an exe, there's no straightforward way to test the code inside the exe. Executables by their nature offer no intrinsic interface for external testing frameworks to hook into. It's more idiomatic to test static libraries instead. Experienced C++ developers know this, so when they start a new project, they know right off the bat to structure their project as one or more static libraries, and then have a separate project to be a thin wrapper which links against the library and compiles it down to an exe. That way, when you add the testing framework, you just link it directly against the static libraries, instead of the exe. Beginners, however, often encounter this architectural insight too late. If you're working on a giant monolithic exe project and you want to add tests late into the development cycle, you'll need to perform a huge refactor to split the monolith into a static lib and a thin wrapper exe. But this can potentially take an enormous amount of time. The only alternative is to go down the rabbit hole of hacky workarounds, like adding a post-build script to your already fragile build system to compile your exe project into both an exe and a static library. Or you have to do some weird trickery with your project settings or IDE to get your files either duplicated or recognized across multiple projects. In the end, you're left wrestling with your build system, or redundantly inflating your compilation times. Even with everything configured correctly, you're still far from operational. Code needs to be written from the ground up with testability in mind, and C++ has its own idioms for making code testable, like compile time dependency injection with policy-based design. And if you're writing postmodern C++, then you're going to want to use policy-based design with the new concepts feature. This can be a lot to grok for newcomers. C++ markets itself as having zero-cost abstractions, though in practice some cracks have begun to show in that promise. Unique pointers, for example, are slower than raw pointers because they get passed on the stack instead of in a register. This is for technical reasons regarding the ABI. Similarly, it seems like string view and span also have the same issue on Windows. C++ move semantics are also not zero-cost, because the destructor of the object which you've moved from still runs. This means that the equivalent handwritten idiomatic C code would run faster. And the fact that move constructors are allowed to throw exceptions means that you incur yet another performance penalty. Rust doesn't have any of these issues because it uses what's called destructive moves, whereas C++ uses non-destructive moves. C++ missed the opportunity to implement destructive moves a few versions ago, and now that the opportunity has passed, it'll likely never have them, in the name of preserving backwards compatibility. And for a language that has a reputation for performance, it's quite lacking in performance-oriented features. For example, you can't choose how objects and collections are organized in memory. There are two main ways in which this can be done: array of structures and structures of arrays. C++ does it the former way, but there are huge performance benefits to doing it the latter way, due to cache efficiency, SIMD optimization potential, and memory access patterns. Not to mention the padding issues with array of structures. It may bloat up the size of your array and hurt cache efficiency even further. C++ has no built-in way to easily declare both layouts with the same interface, or convert between the two layouts, or access the data with the same syntax regardless of the layout. Instead, you need to painstakingly implement all this yourself, which leads to duplicated code, error-prone access patterns, and complex template metaprogramming, which is difficult to maintain. I'm hoping that Reflection in C++26 will be able to solve this elegantly. Another example is floating point math. There are ways to improve the performance of floating point math by relaxing the very strict rules of the floating point standard. Some compilers have a flag to enable this performance boost, but it applies it indiscriminately across the entire codebase. There's no simple way to selectively turn it on for some functions but not for others. There's also no built-in support for auto-differentiation, which is crucial for many modern algorithms, particularly in machine learning. It's a technique for efficiently computing derivatives, but for maximum performance and practicality, it needs to be integrated directly into the compiler optimization pipeline. There's many other things as well, like if you're passing something to a function, it can be faster to pass by value than by const reference for certain types. But rather than trying to guess which technique to pick, there should be a way to prompt the compiler to pick whichever technique is faster for the given type, because developers tend to underestimate the size of the type that would be faster to pass by value. It would also be nice to have finer-grained control over lifetimes, like the ability to activate destructors on last use instead of scope end. SIMD support is also lacking in C++. At least SIMD has been voted into the standard library in the upcoming C++ 26, so we'll get that soon. But as for the others that I've mentioned, I'm not so sure. That being said, some of the stuff that actually is in the standard library is incredibly poorly optimized and stuck that way forever. The regex implementation is notoriously slow. It's regarded as being one of the worst regex implementations in existence. Some benchmarks show that it's 10 to 100 times slower than other implementations. It's absolutely comically slow. It's a complete failure of an implementation. Earlier I mentioned that you probably shouldn't use unordered set and unordered map. The reason why is because they're also very slow, because they use cache-unfriendly linked list buckets for hash collision resolution. If you care about performance, you need to use third-party implementations, like flat hash set and flat hash map from Google's AppSale library, or F14 from Facebook's Folly library. Or if you want a header-only implementation, you can use the implementation from this GitHub repository. There's an ever-expanding list of things in C++ that could have their performance improved significantly, but it'll never happen because of ABI backwards compatibility concerns. And that's what's perhaps the biggest lie of C++. People think of it as a language that prioritizes performance, when in reality it prioritizes backwards compatibility over everything. Performance, ergonomics, developer experience, everything. Its adherence to backward compatibility is what has turned the language into a monster. And perhaps the biggest issue with its performance is how heavily it relies on compiler optimizations. C++ is a poorly designed language that leans heavily on compilers to compensate for its shortcomings. To say that compilers optimize C++ is an understatement. Compilers literally rescue C++ from its poor design. The most basic example of this is copy elision. This is a compiler optimization to eliminate redundant copying of objects. The reason why we need this is because the default behavior in C++ is to pervasively make copies literally everywhere that it can. Here we're just calling two functions, yet it's performing 4 copies. Now try to extrapolate this to a real-life codebase. You could end up with tens of thousands or millions of unnecessary copies. So we need compiler optimizations like copy elision to come in and clean it all up. Copy elision is so fundamental to C++ that it still runs even if you disable optimizations. Optimizations like RVO, NRVO, and the whole apparatus of move semantics are a convoluted set of workarounds to avoid the cost of obeying the language's own semantics. This dependency that C++ has on compiler optimizations also leads to other problems as well. Namely that you can't see compiler optimizations in the code, and you have no guarantees that a particular optimization is even being performed. The developer has to cross their fingers and pray that the compiler will perform the optimization. This is very unreliable. Take tail call optimization for instance. If you write a recursive function, it can blow out your stack. But with tail call optimization, it keeps reusing a single stack frame by updating the parameter values in place and jumping back to the beginning of the function. In other words, it uses constant stack space regardless of recursion depth. Allegedly, modern compilers are good at optimizing this. Allegedly. The issue is that you can't see it in the source code. C++ is way too dependent on opaque, unreliable compiler optimization wizardry instead of language constructs. You can't look at a piece of C++ code and say with certainty what will happen at the machine level. This forces you into a superstitious relationship with the optimizer, where you must assume or hope that optimizations will occur, or write contorted code that nudges the compiler into doing the right thing. A well-designed systems language should make performance a property of the source code, not a side effect of compilation. The correspondence between code and cost should be predictable. You should be able to reason about the performance directly from the structure of the code. If C++ was less reliant on compiler optimization because it had better language design, then you'd be able to see exactly what's going on in the source code, and unoptimized debug builds would run faster, and there would be less discrepancy in the behaviors between debug builds and release builds. The current state of affairs forces developers to create at least one more build mode that's a hybridized Frankenstein of debug and release to try to address these issues. Simply put, C++'s reputation for speed is not a triumph of its design, but a testament to the extraordinary efforts of those who build its compilers. Let's talk about job opportunities. People seem to think that because C++ is so difficult to learn, it must be the case that the pay is really good. But the answer is not so simple. Obviously, there are a lot of factors that influence pay, such as your location, skill, and domain. Generally speaking, passion-driven domains like video games are poorly paid, and they skew the salary statistics downward. The financial sector pays a lot higher, but can be highly competitive with crazy work hours. Overall, if you exclude video game development, it does seem like C++ jobs generally do pay a bit better on average in comparison to other languages. However, you have to call into question if that extra pay is worth it given the difficulty of the language. Web development can pay pretty well too, and there are more job opportunities in web dev. It's also easier to hop from one job to another. In contrast, if you have a computer vision role in C++, you can't just switch to a completely different domain like high-frequency trading, so you sort of get pigeonholed into a particular specialized field. Sometimes system programmers feel like they're better or smarter than web devs, but honestly, there's an argument to be made that it's actually better to be a web developer. You can get better work-life balance, and it can be more flexible with more potential for remote work. You can get really good at web dev in only a few months, and start building incredible dashboards and fully functioning web apps that you can actually show to people, while at the same time you have time to go out for drinks with your friends and have hobbies and socialize and find a partner and start a family if you want. Or you can spend like 2.5 years on C++, and all you have is a triangle and Vulkan. The truth is that while the C++ developer is optimizing their code, the web developer is optimizing their life. Web development is also typically situated higher up in the business hierarchy than C++, which means that web developers are more likely to collaborate with product managers, designers, marketing leads, and even executive stakeholders. This gives them greater insight into high-level business priorities, and also positions them more favorably for upward mobility into leadership or cross-functional roles. In contrast, C++ engineers are often confined to doing infrastructural work like maintaining legacy systems or optimizing low-level libraries that, while mission-critical, remain largely invisible to non-technical leadership. This has a tendency to constrain their career trajectory and influence. The other problem with C++ is that when you start using it, you can't stop. You're only productive with the language if you're using it every day. If you take any significant amount of time off, your skills are going to atrophy very quickly. It's also important to understand that while C++ can be fast at runtime, it has incredibly slow development time. It takes a very long time to ship a product or add a new feature to an existing product, and there are many projects for which the time you spend optimizing your code will be more than what you gain in runtime performance. Sometimes in life there are these fleeting little windows of opportunity that present themselves to you, and it's imperative that you capture those opportunities before they're lost forever. It takes a really long time to make software with C++, and what you may find is that by the time you're ready to ship your product, the opportunity has passed, technology has evolved, and the world has moved on to something else. Anyway, so what's the verdict? Overall, C++ is a very fast language, and it's highly backwards compatible with good interop with C. It's also flexible, in the sense that it supports multiple programming paradigms. It has some excellent features and paradigms like RAII and powerful metaprogramming capabilities, which are a step function improvement over what's available in C. The language is constantly being improved on, and some of the new features which attempt to modernize it are pretty good. There's also billions of lines of code written in C++, so it's basically used everywhere, and as a result has an enormous ecosystem and incredible momentum. That being said, building a non-trivial project can be excruciating. Dependency management is atrocious. Compile times are unacceptable, errors are incomprehensible, the code is obnoxiously and gratuitously verbose, and every codebase looks different. It's also not verbose enough in places where it should be, like conversions and copies. The language is unfathomably complicated. It's incredibly difficult to write code correctly. It has terrible defaults. It requires an exhausting amount of boilerplate to do simple things. The standard library is incomplete, and some of the things which are available in the standard library should have been built directly into the language itself. There are a lot of hard-to-use features which will cause bugs or undefined behavior unless you're following certain rules which aren't enforced by the language or compiler. One bad line of code can take down a 10 million line codebase and be agonizing to debug. There's way too many footguns. It's accumulated way too much historical baggage. Safety remains fundamentally unresolved, and although some of the new features are decent, most of them are awkwardly bolted on as an afterthought and are painfully unergonomic with a lot left to be desired. The final verdict is that C++ is a horrible language. It's completely lost the script. Using the language is a literal torture. It's an infinite Gordian knot of unfathomable complexity. The cognitive burden is untenable. You need an encyclopedic memory to even stand a chance at using it correctly. But just because it's a horrible language doesn't mean that you shouldn't use it. Bjorn Stroustrup, the creator of C++, famously said, "There are only two kinds of languages, the ones people complain about and the ones nobody uses." On one hand, this is a completely tone-deaf thing to say, because C++ has more problems with it than all the other popular programming languages combined. And the grievances surrounding the language aren't just little nitpicks about syntax, they're about deep, fundamental core design failures. The only appropriate response to this is cope. Your language sucks. That being said, there are many fields where you have to use it. You don't have a choice. So let's talk about who should learn C++. First of all, I would absolutely never recommend it as a first language. It's way too inhospitable and unforgiving to beginners and experts alike, but especially to beginners. If you have at least some programming experience, you might consider learning C++ if you're interested in a field where it's dominant, like automotive or high-frequency trading or robotics, or if you want to start a new project that requires high performance and you want better abstractions than what C has to provide. Or maybe you want to use some highly critical libraries that are only available in C++. Just be sure that you really need it before you commit to it. Sometimes you'll hear that machine learning is done in C++, but that's not really true. The libraries are written in C++, but people generally use them from Python. So try to see if you can use a different language instead of working with it directly. Additionally, you're also a good candidate to learn C++ if you have a lot of free time. If we compare C++ to other languages like Go, which are designed from the ground up to be as simple as possible, the general consensus is that if you are an experienced developer, it takes about 1 month to become proficient in Go, whereas it takes 3 to 6 months to become proficient in Rust, and about 2 to 5 years to become proficient in C++, depending on which field you're in and how you learn it. Keep in mind, this doesn't imply mastery. It's just the amount of time it takes to become effective in using the language. And don't take these numbers too seriously, I don't have any studies to prove this. It's just napkin math based off of general consensus. Anyways, as C++ gets more and more features bolted onto it, it may take 3 to 6 years to learn it, and then 4 to 8 years to learn it, and then inevitably a decade to learn it. Future versions of C++ are going to require a prohibitive amount of time to learn properly. People are inevitably going to end up only learning some subset of the language, but I doubt there's going to be any consensus on which subset of the language to use. The most important thing is that if you're going to use C++ to work on something, you better pick a project which you're super passionate about. Because after years of wrestling with the language, if you're unhappy with your project or if your project is unsuccessful, you may come to the sobering conclusion that you just wasted your life. I personally ended up writing C++ because I had no choice. I had a really bad case of RSI in both of my arms, and there was no good computer vision system to help with performing mouse actions without using a physical mouse. Necessity is the mother of invention, so I created a program called NeverClick, which lets me do just that. I can conveniently click on things on the screen using just my keyboard. I can do left clicks, right clicks, even dragging and highlighting, and it's way faster and more accurate than using a physical mouse. It's also super cozy being able to navigate code and browse the internet without moving my hands away from the keyboard. And my hand pain actually went away, and I have my life back now. C++ was the only language that was able to deliver the performance needed to get NeverClick working in real time. If you also have hand pain or you're interested in NeverClick, let me know in the comments. I'll release it to the public if enough people care about it. I might make a Discord chat for it too, so check the description or comments section if you're interested. Anyways, back to C++. Some people choose to learn C++ because they romanticize the complexity of the language, or they want to prove they're smart or something. This isn't a good reason to learn the language. Keep in mind that a lot of the complexity behind C++ is just specific to C++, as opposed to being inherent to the nature of computers and how they work. The complexities are there either for historical reasons or for backwards compatibility, or they exist as weird hacks and solutions to fix problems that the language created itself. You're just going to end up filling your brain with arbitrary language-specific knowledge that has no rhyme or reason. Some concepts will transfer to other languages, but a lot won't. In terms of how to actually learn C++, most of the resources for learning C++ that show up near the top of Google search are really bad. The general consensus on internet forums is that learncpp.com is probably the best free resource. But if you like influencer-style videos, I'd recommend the Cherno. When you get into super advanced C++, then the final destination for that is either CPPCon or Jason Turner's YouTube channel. But some of the concepts that they talk about here are so next level that you need years of C++ experience just to understand what the title of the video even means. Regardless, no matter what road you take to learn the language, if you have even a modicum of self-respect, you will come to hate it. But the journey is so long that those insights may arrive too late, and all that time is wasted. While I've been sitting here debugging segmentation faults, all my friends got rich in real estate and crypto and dropshipping and mobile and web apps and other ways which I won't mention. If you choose to learn C++ anyway, mark my words, one day when you're working late into the night, searching for that elusive bug in your codebase, you will come to the realization that there is no bug in the codebase. The bug is you. You are the bug. C++ was not created for humans. It was created for aliens or infallible, super-intelligent AI systems from the future. Any situation where a human is writing C++ code is one which will end in disaster. Before I end the video, I'd like to touch on Rust, given the fact that it's become a promising competitor to C++, and the fact that there's a trend of people rewriting C++ projects in Rust. Rust does have some incredible features. The first is that it's highly performant. It's comparable to C++ in terms of how fast it is. But unlike C++, everything is standardized. It has a standard compiler, a standard build system, a standard package manager, and a built-in standard way to write tests. So it's a breeze to start a project and build your code and install and use libraries and write tests. There are no header files, it uses a proper module system. It has absolutely phenomenal error messages, not just compared to C++, but compared to any language. In contrast to C++, though, it has excellent defaults, no implicit conversion, and it has UTF-8 support. It has excellent tooling with a much faster language server, linter, etc. It has a lot of wonderful features that are built natively into the language, like sum types, which rivals C++ variants, and they have excellent IDE auto-completion support. Using enums in Rust will completely spoil you and make you hate other languages for not having it. Also, C++'s standard move is built directly into Rust by default. The standard library is smaller than C++'s, but the stuff that it does have is way better. Like its hash map implementation is one of the best of any language. It completely smokes C++'s standard unordered map. And serializing into JSON is really easy with libraries like Serd. There's many other things too, but perhaps the most important feature is that it's safe. Some people will say that modern C++ has made great strides in becoming safe too. Features like smart pointers have solved problems like memory leaks, dangling pointers, and double freeze. But new features like lambdas, string views, and ranges have only introduced more memory safety issues. And modern C++ hasn't fixed the problems of uninitialized memory, use after move, null pointers, dangling references, out-of-bounds access, iterator invalidation, data races in multi-threaded programs, and lambda capture lifetimes. It doesn't even hold the prospect of fixing these in the next 10 years, whereas in Rust, these issues are resolved today. Rust isn't perfect though, it is lacking in some areas. Its ecosystem isn't as mature and extensive as C++'s ecosystem. A lot of important technologies like CUDA still have better support for C++ than for Rust. Also, game engines and games are predominantly written in C++, and it looks like it's going to be like this for a very, very long time, because Rust's emphasis on safety and correctness fundamentally conflicts with game development's need for rapid prototyping and iteration and creative experimentation. There's a growing pile of Rust games that are abandoning Rust. Rust has something called a borrow checker, which enforces memory safety rules at compile time. It's a wonderful feature, but sometimes it may force you to completely redesign and refactor your code at the worst time possible. If you're prototyping something, you may not care about writing perfect code, but the borrow checker is very strict and it will care about that. If I had to list out some other shortcomings of Rust, it seems that metaprogramming in Rust isn't as powerful as in C++, at least for now. And despite not using header files, it does have slow compilation times, probably due to the borrow checker and lifetime analysis. I'm sure that this will improve in the future though. Rust has a subset of the language called unsafe Rust, which allows you to bypass some of the language's memory safety guarantees in order to give you more low-level control, but it's a bit unergonomic to use. In other words, it's more restrictive and difficult to write than the normal C or C++, and the syntax is more awkward. There are at least a few things in Rust that are considered to be more difficult than in other languages. Async Rust is allegedly really hard. Also, circular and self-referential data structures are really hard to write in Rust. And even though the package manager is amazing, it has the same issues as NPM, where you install a package that needs to install like 100 other packages. This can pose a security risk, especially for a low-level language like this. And although Rust has thousands of packages to choose from, many of them are incomplete, poorly implemented, or abandoned before they even hit version 1.0. C++ is still able to target more machines than Rust, because Rust is dependent on LLVM, whereas C++ can also use LLVM via Clang, but it also has other compilers to choose from too. Also, since Rust does bounce checking at runtime, there's some debate about what the performance penalty of this is in practice. And lastly, it's still a nascent technology, and although it's catching on, there still aren't a lot of job opportunities for it. Overall, my verdict for Rust is that, despite the shortcomings, it's actually fantastic. It's an absolute breath of fresh air. It fixes so many issues that C++ has, and although there's been many other alleged C++ killers in the past, Rust stands as an actual viable alternative to C++. The design of Rust is orders of magnitude better than the design of C++, and the developer experience is phenomenal. But just because it's better doesn't necessarily mean that you should use it. Languages don't exist in a vacuum. C++ has the benefit of being around for much longer, and as a result, it's become ubiquitous. Rust has continued to grow without faltering. I think it could potentially grow even faster, but one of the things that adds friction to its adoption is that you sort of need experience in C++ to truly appreciate and understand the problems with C++ that Rust fixes. And also, most programmers are web developers who don't care about low-level languages. And there's also a popular video game called Rust, which can mess with your internet search results. Ultimately, I do think that Rust is a step function improvement over C++, but regardless of what I think, it's very clear to a lot of people that C++ is a problem. And in recent times, there's been a lot of active development in alternative languages. This raises the question, is C++ dying? The answer is no. Even though it's a terrible language, it has so much momentum. The entire world runs on it. It'll likely be relevant for decades to come. Maybe in the future, AI will effortlessly rewrite existing C++ code bases in a better language. Maybe AGI will create a new programming language, which will be the perfect language that we can all love and use. But for the foreseeable future, C++ is unfortunately here to stay. Let me know in the comments if I missed anything, and tell me, what do you think of C++?